Hi, neighbor. I'm Carol Nichols or Goulding on Twitter at Carol's 10 Cents. And today, let's find out what's special about Rust. All right, so who am I? I am a member of the Rust core team. I am the co-author of the Rust programming language book, and I'm the co-author of the Rust in Motion live video series. I'm also a former Ruby programmer before I started learning Rust. And I also have a 2-year-old daughter named Vivian. And here's where I wish I was giving this in person so I could hear everyone go, "Aw," because she's just adorable. Okay, so why was I singing at the beginning of this talk? I was singing because my daughter and I love to watch Daniel Tiger. And Daniel Tiger is a kids show that is an animated spinoff of Mr. Rogers' Neighborhood. The main character is Daniel Tiger, and he is the son of Daniel Striped Tiger, who is the puppet who is on Mr. Rogers' Neighborhood, and now he's Dad Tiger. It's a really cute show. They do a lot of research into child development before they develop the episodes, and they're mostly about dealing with different kinds of feelings. And every episode has a strategy song to help you remember how to deal with those feelings. It's a really great show, and it's one I actually enjoy watching with my daughter. And in acknowledgement of the time that we are all spending blending work and family time a lot more than we usually do, I decided to do a Daniel Tiger themed Rust talk. So in this talk, I'm going to be telling you something special about Rust with a Daniel Tiger song parody. So I hope you enjoy this. If you don't know Daniel Tiger or don't have any desire to know anything about Daniel Tiger, you're not going to miss out any Rust knowledge in this talk. You're just going to have to listen to me singing for no good reason every once in a while. So, and I hope if your kids are watching this with you, and if they like Daniel Tiger, that they enjoy this. And if it makes them say, "That's not Daniel Tiger, but that's Daniel Tiger song," and they want to watch Daniel Tiger instead, I totally understand. And I'll see you after bedtime. All right, so our plan today is we're going to go through 5 good things about Rust, 1 bad thing about Rust to be even-handed here, and then 1 more thing. Okay, so our first good thing is that Rust is an empowering language. And in other words, I mean, everyone is big enough to do systems programming. Traditionally, systems programming has meant that you're programming in C or C++ so that your code runs fast and doesn't use a lot of memory or time spent from the CPU. But in order to get these advantages, you have to trade off the memory safety that higher level languages give you with garbage collection, and you have to manage the memory yourself, which tends to lead to memory unsafety problems, such as use after free, where you clean up memory that you're managing manually, and then you try to use it again. Double free, where you clean up memory twice, and that can lead to memory corruption. Buffer overreads and overwrites, where you access beyond the end of your data structure because you're doing pointer arithmetic, and your code is accessing memory that it shouldn't be accessing. And null pointers, where you think you are pointing to some valid data and actually you're pointing to nothing, and you either have to check for that case everywhere, or if you miss a check, you might be trying to do something with nothing. A lot of programmers, I should be nowhere near production C or C++ because I do not know everywhere that I might be writing memory unsafe code. and there's a lot of corner cases and weird parts of C and C++. You have to be an expert in C and C++ to be writing production level code. But so people seem to say, I've seen people say that, oh, programmers just need to be more careful. And if they were more careful and knew more, then we wouldn't have all these memory unsafe problems that lead to crashes and vulnerabilities and exploits. But we've had C for 40 years, and we have seen that being more careful does not work. Humans are not capable of being careful enough to write safe production C and C++. The proof that I have for this is that both Microsoft and the Chrome team have come out with articles where they've analyzed all the security bugs that they've had in Windows and in Chrome. And both of them have found that 70% of their security bugs have been due to memory safety issues. And the fact that both of these companies are large and able to pay for experts in these programming languages, and they're able to get the most careful programmers, yet they still end up with 70% of these security problems caused by memory unsafety, says to me that there's no way to fix this 70% by being more careful. We need to do something else. And you might think, well, maybe we should make C better. But there's this great article that I recently saw from John Heydmanid called "Why the C Language Will Never Stop You from Making Mistakes." The short answer is because the C Standards Committee has decided to value backwards compatibility over fixing problems or warning you of mistakes or stopping you from writing code that might be memory unsafe. And that's a perfectly valid decision to make for the language, that backwards compatibility is the most important thing. It's just that I don't see myself spending enough time to even be a halfway competent programmer in C to get fast, low resource usage code. And that is where Rust comes in. Rust is a systems programming language. It's been stable for 5 years now. And it also runs fast and is able to use low amounts of resources, but it doesn't have the memory unsafety problems by default. It is a memory safe language unless you choose to opt out of it in certain areas at certain points very explicitly. This memory safety is guaranteed at compile time. Rust won't even let you compile, let alone run, code that violates its memory safety guarantees. And these guarantees apply across multiple threads. So writing multi-threaded C and C++ is even another level of expertise that you need to have and not many people are capable of. But in Rust, the compiler helps any programmer write systems programming code. And I'm not saying that Rust prevents all mistakes. What I am saying is that we have these old mistakes in C and C++ that we know lots about. We've seen them over and over and over again. And all I'm saying is that let's stop making the old mistakes so that we can make some new mistakes. The other way I like to think about Rust is that it makes memory safety the compiler's responsibility, and computers are extremely good at keeping track of tedious details that are involved in ensuring memory safety. And that leaves me free to concentrate on my domain logic, what my program should actually be doing, what a human needs to understand about my code. And that is really freeing and lets me do what I'm good at and lets the computer do what it's good at. Which brings us to the second good thing about Rust, ownership. This is how Rust ensures that there's memory safety at compile time. And you can think of ownership as clean up, pick up memory, clean up what you own. Ownership is a system in Rust where there is one owner of each piece of data, one variable designated as the owner. When the owner of that data goes out of scope, the data gets cleaned up, and you don't have to write free or explicitly say that in your code. The owner of a piece of data can transfer ownership to another variable, or it can lend out that data, which is borrowing, and we'll talk about borrowing in a minute. Let's take a look at this in code. This is a main function in Rust, and we are creating a variable named x, and we are putting an allocated string in, and it is going to be owned by x. This string from allocates memory on the heap, and we could grow this string if we wanted to. X is the owner, and when the owner goes out of scope at the end of main, the memory allocated for the string gets cleaned up. The code that does the cleaning up gets inserted at compile time by the compiler, and there is no garbage collector running at runtime to do this cleaning up. So let's take a look at a situation where we transfer ownership. In this code, we have the x with the allocated string again, and then we say let y equals x, which transfers ownership from x to y. Then in the next line, we try and print out x again. And in many other programming languages, the third line in the body of the function would work fine, and we'd be able to print out the value of x. But in Rust, this is a compile time error because we've moved ownership from x to y, and after that point, x no longer has access to the memory that it used to own, that's now y owns. This is important because at the end of the function, y is now responsible for cleaning up the memory, not x. So there will only be one, and only be exactly one, cleaning up of the memory that was allocated. That gets rid of the double freeze and use after freeze and various problems like that. This code might look a little inconvenient though if you're used to being able to have use of x after assigning it to y. Which brings us to good thing number 3 that Rust has, borrowing. You can borrow memory and then I'll get it back. Borrowing is a way that an owner can let some other part of code read or write to that data without transferring ownership. And you do that with an ampersand. This might look like a reference, and this might look like a pointer that you might be familiar with other languages. In Rust, this is called a reference. And another way to say it is that this is an immutable borrow that y has of the data that is still owned by x. With y having a borrow of the data in x, then we are able to run this code that accesses both the memory at x through x and through y, accessing the same heap memory with this immutable borrow. Now, there are lots of problems with pointers that references in Rust don't have. For example, in this code, if this was, so what this code is doing is we are creating a new variable named y, and we're assigning it to the result of this new scope in the inner curly brackets. In there, we are creating variable x that allocates some heap memory, And then we are trying to return a borrow to that memory from that inner scope to the outer scope. The problem with this is that at the end of the inner scope, X gets cleaned up and Y would have a reference to data that doesn't exist anymore. If we try to compile this code with Rust, we get an error that says X does not live long enough. That we are trying to store a borrow in Y, that it gets cleaned up, the value that it's borrowing gets cleaned up before we try and use this. So Rust won't even let us compile this code. Which brings me to good thing number 4 about Rust, which is the error messages. When you feel so mad that you wanna roar, take a deep breath and read the compiler messages. 1, 2, 3, 4. You may have looked at that error message, and you may have looked at error messages in the past when you're trying to get your code working and just gotten really mad that your code was not doing what you wanted it to do. And I know I've done this. You are frustrated and you just want to get it to work, and you switch back from your terminal to your editor and you start trying to change things and getting it to work. And you might be guessing what's wrong. You might have looked at the error messages and they're not helping, so you're just going to ignore them. But in Rust, a lot of work has been put into the error messages to actually make them useful and helpful. And that means in Rust, when you get an error message, even though you might get a lot, and they might be really long, they should be helpful in explaining what you need to do to change your code. And if they're not helpful or they're not clear, we consider that a bug. So I wanted to go through a few examples of amazing compiler error messages. In Rust, there is a construct called match, which is sort of like a switch or a case statement, but it has some pattern matching that you might know from languages like Elixir or Erlang. And in this particular match statement, we are checking the results of 2 functions that return Booleans, is logged in and is admin. And you can imagine an application where you might be logged in as a regular user, you might be logged in as an administrator user, and we want the application to do different things based on those 2 pieces of information. If you are logged in, but you're not an admin, we will display a dashboard. If you're logged in and you are an admin, we'll show you the admin settings. And if you're not logged in and you're not an admin, then we'll display the login page. Now, the problem with this match statement is that we're missing a case here. We are missing the false true case. So if we try to compile this match as is, we get an error that says we have non-exhaustive patterns, because in this case, Rust can tell that we missed a case. And it even tells us which one we missed. We missed false true. And it points to our exact code and shows where the expression is that we're not matching all the possible patterns. And it says you can possibly fix this by adding wildcards or more match arms. And it even tells us what the type of the value is that we're matching on. So knowing this, we can go back to our code and take a look and say, okay, what should we do for the false true case? And in this case, it really doesn't make any sense to be not logged in, but be an admin. So what we want to do is the same thing as false false. And we can do that by creating a catch-all kind of case and handle both the remaining cases by matching anything remaining and displaying the login. In this next example, I have a variable with a number in it, and then I have an if statement where I have forgotten to do double equals. I just have a single equals in the if count equals 20. And in some languages like Ruby, that I'm not saying I've done this before, but I might have done this before. This would actually assign to the count variable and happily continue on and do something that is not at all what you're expecting. And there's no real indication that you're missing an equal sign in where you mean to be comparing. So this is this problem. If you try to compile this in Rust, it says mismatched types. It says expected bool because Rust is strongly typed and all expressions in ifs have to evaluate to booleans. It found empty parentheses, which is the unit type, which is kind of, there isn't really a return value because assignment statements don't return anything in Rust. And it has some help text saying, maybe you wanted to compare for equality with double equals here, just a guess. So then we can go back to our code, put in that extra equal sign, and be on our way. So I really love Rust error messages, and it makes me sad when people don't read them because they are actually really helpful. And I really appreciate all the work that has been put into making them that way. And I think that's pretty special. The next special thing I'd like to talk about is special thing number 5, the Rust community. Rust friends help each other, yes they do, it's true. There are lots of things I love about the people who work on Rust and the people who use Rust. One thing I really appreciate is that there's been a documentation culture from the beginning. There's been a lot of emphasis on producing good documentation. Lots of the libraries that people have released, the ones that are most popular have great documentation, and people notice that and want to create other crates that have great documentation. There's lots of tutorials, there's lots of books, and we really, because Rust is made up of people who have felt left out of other systems programming languages because they're so hard to learn, I feel like we really value going the extra mile to help other people come into the Rust community. Another important part of the community is that Rust has had a code of conduct since it was first open sourced. And we also have, it's not just words, we have a wonderful, amazing moderation team, all volunteers who do a lot of work to ensure that our code of conduct is upheld. We're not perfect by any means. There have been problems, there will be more problems, but we are made up of people who value a professional community where everyone is treated respectfully. And that's really important to me. The other thing that's really important about the community and how the community works on Rust is that major decisions and major changes are made through this open decision-making process called the RFC process, request for comments. And it can be really tiring because it's kind of talking with everyone and building consensus, and that takes time and it's difficult sometimes. But even when the consensus is not what you'd want it to be, at least you are able to see what the rationale is for that and see what the trade-offs were because we've talked about them all in the open, and appreciate why the language or crates or other parts of Rust might have made that decision. It's different from other languages that are kind of developed internally and then open sourced after the fact, where you're like, why is this way? And there's no way to figure it out. With Rust, there's often a whole history of how that decision was made and the factors that went into that. that you can look at and explains why things are the way they are and where they could be improved. And there's a mechanism for you to participate in that process and make changes. And I find that to be really special and really important. Okay, to be a little bit balanced here, because clearly I love Rust, I'm gonna talk about one bad thing about Rust, which is that prototyping a program can be harder in Rust than you're used to in other languages, like maybe Ruby or Python, where you can just kind of write out a shell script, or sort of write out a script of some sort to do a task very quickly. What this might look like is you get to work and you say, okay, I see what we have to do here. We just have to take this data. We're going to move it over to the system over here and transform it a little bit. Then we're going to move it over here and display it. And I know how to do all that, and I'll be done by the end of the day. What Rust sees when it looks at this code that you want to write is that it says, what if this data is malformed? What do you want me to do then? And what if a bear comes in over here and eats your data? It might happen. What do you want me to do about that? And what if your display just isn't there? We have to handle that somehow. And oh, you think you're going to be done by the end of the day? No, I don't think so. I need to know how we're going to handle all these problems. And you might not be ready to handle all this problem. You might not know what to do with all these problems. You just want to get the happy path working, and Rust can get in the way sometimes with that. There are ways around it. There are ways to explicitly stop your program if it encounters certain kinds of errors instead of handling it, which safely just kind of stops your program and exits and doesn't let you continue in a bad state, which in production code, you don't want to be crashing most of the time. So you do want to go back and handle those places. But because you have to be explicit in Rust, you do have those places you can search for, the places where you've explicitly ignored or delegated the error handling for those cases. And when something seems bad, turn it around, find something good. The way I like to think about this when I'm running into it is that sometimes it's good to code slow. How many times have you heard this at work? No, this is just a prototype. We don't have to handle the errors. We don't have to think about that. We're going to throw it away. We're just trying this. And then you get it working, and then people start saying, oh, this is wonderful. It does exactly what we want. We're going to put it in production. And suddenly your throwaway code isn't so throwaway anymore. And that can make a big maintenance burden to redo that code while it's running instead of throwing it away. So sometimes I think it's good that Rust slows you down and makes you acknowledge at least the error cases that might happen, so that when you get in this situation where you're ending up supporting code that you didn't think you were going to support, at least you have those places in the code to go back to handle the errors that you explicitly ignored. Okay, it's almost time to stop, so choose one more thing to talk about. I couldn't quite fit this last thing into the Daniel Tiger theme, so I'm just kind of sneaking in here at the end. Another really big thing that's special about Rust is its tooling. And specifically, I want to talk for a little bit about Cargo. Cargo is the build tool for Rust code. It is a test runner, it's the dependency manager, and all of those functions work together, ensuring that the majority of the Rust programs that you can find on GitHub, you can pull them down and just run Cargo build and Cargo test, and it will work. It will be able to fetch all the dependencies and build all of those, and you can be off and running. C and C++ don't really have dependency management, and Cargo has learned a lot from Ruby gems and Bundler and NPM and Yarn, and has brought those modern tooling to the systems programming world. And this is a huge thing that makes me love Rust. That was fun, and now this talk's done. Thank you, neighbor, for having fun with this talk with me. I hope you enjoyed the Daniel Tiger songs and learning about Rust. Have a great day. Ugga mugga.
Hi, I'm Maciej. I work at Parity Technologies, where we do stuff with blockchains, and the thing that is often involved in blockchains is cryptography, so crypto for short. And in this talk, I'm gonna just briefly talk to you about how we use Rust for cryptography, and specifically how we use Rust for crypto on mobile. So a short overview of what we're going to cover here. First, I'm gonna just give you a brief description of what the party signer, which is the app that we're going to talk about, how it's using the cryptography. Then we're going to briefly talk about what two specific crates we are using for Rust, and why we are doing that. Then we're going to actually show you how we are embedding the Rust into a React Native app. So party signer is written in React Native. And finally, some closing thoughts and comments that might be useful to you if if this is something you want to do, if you want to embed Rust in mobile, if you want to use some crypto, or go there in any way, shape, or form. So let's begin. What is a party signer? The short answer is kind of confusing, and it's confusing because the word wallet in blockchain is an extremely overloaded term, and means a lot of different things to a lot of different people. So as such, I can tell you it's an app that is intended to turn your phone into a hardware wallet, but that's not necessarily very useful, especially not if you never had any contact with blockchains or cryptocurrencies or stuff like that. So a bit more verbose, and but also like more accurate description is that it's an app that you can use to generate, to store, and to use a secret key for cryptographic purposes. And that this app by itself is not very useful. It needs a second app and a second device to actually do useful stuff with. And it uses QR codes to communicate with that second app and the second device for security, basically. So the app is intended to run on a phone, and it's intended to run on a phone that's completely offline. And therefore, the QR codes are the means of communication. And lastly, it's worth mentioning the app itself is written in React Native, which for our purpose here is irrelevant because it defines how we are going to do the bindings, and actually makes the bindings themselves a bit more difficult. For those who don't know, the React Native is a framework with which you can develop mobile applications. This framework is using the very popular JavaScript library called React for building websites, and it is indeed running a JavaScript runtime on your phone. But instead of using actual like browser, HTML elements and stuff like that, the React Native is actually mapping React components to native, therefore the name, UI elements for either iOS or Android. Right, so that's a very high-level view of what React Native is, and for our purposes, it's just worth just think of it as just a JavaScript runtime that we need to expose code to in order for all this stuff to work. So let's talk about Rust crypto. So blockchains tend to use elliptic curve asymmetric cryptography. The way this works is, if you never heard about asymmetric cryptography, you have a private key, you have a public key, secret key and public key. The secret key is secret, so you should be the only person that has a copy of the secret key. And the public key can spread around. You can give it to your friends or strangers, doesn't really matter, everyone can have one. And what you can do with elliptic curve cryptography is you can create signatures. So you can take basically any arbitrary blob of data, and using some math and your series of bytes, which is your secret key, you can create a signature for that blob of data, right? So this can mean a lot of things. And then anyone who has that blob of data and has your signature and also has your public key can verify that this signature is valid for this block of data for this public key, which is tied to the secret key from which was generated, right? So it's a one-way thing where I can create a signature and you can verify it, but you cannot create a signature just with a public key. If you think of something like Bitcoin, then that's reasonably easy. The most common thing we want to do on like a blockchain like Bitcoin, you want to send someone some money. So you have Bitcoin accounts. The address of the account is actually a derivative of the public key, which is the derivative of the secret key. That's basically is the proof of ownership of assets on that account. All right. So if Alice wants to send Bob some Bitcoin, Alice needs to create a signature for a transaction to Bob, and then broadcast that signature with the transaction to the network, and then miners and everyone else who is interested, but mostly it involves miners, can take that transaction, include it in block, and then verify that yes, it is indeed Alice who has signed this transaction, and therefore this transaction has access to the funds there, and therefore can move the funds somewhere else. Very briefly, so for our purpose, we are using two different crates, and that's because we are actually supporting multiple networks on the party signer. So the first is for the SEC P256K1 elliptic curve cryptography. We are using the libsec P256K1 crate, so easy to find on crates.io. This is basically the curve that's used on Bitcoin, but for our purposes we are using it for Ethereum, which is what Ethereum is using. So that's what we have to do. We also have another elliptic curve called ED25519, and for that we are using a crate called Snorkel, and Snorkel implements the ED25519 with some extra compression that enables some extra features. And if all of this is extremely confusing to you, you're in good company, because this is stuff, most of the stuff of how this actually works and how the math actually works is of interest to cryptographers, is not necessarily of interest to developers. If you are a developer, what you might be interested in is basically what are the properties of the different curves, what are the advantages or disadvantages. So in our case, the reason we are using ED for Substrate, which is our new blockchain building framework that we also build our own chain on top of, which is called Polkadot. Snorkel allows us to verify multiple signatures in a batch, in a single block specifically. So speed up the verification. So for our purposes, it's actually better. It's also newer. But yes, for you as a developer, you don't really have to understand the math necessarily. It's good to have some rudimentary understanding of how the math works, but it's absolutely necessary for using them. All you have to do is understand how to use the libraries correctly, and how avoiding some security issues around actually just using secret keys in memory, and especially if if your device is shared and stuff like that. There's some extra stuff we are also using Rust for, since we are if you are already embedding Rust into something, we can maybe find other uses for it other than just cryptography. So we also use hashing, which is also cryptography, but not signatures. But we also do things like we are generating QR codes and identity icons. And those are basically just very, very quickly generated PNGs. They're generated in Rust. And they're actually, for our purposes, actually faster to render a PNG in the UI than it is to do some extra work in JavaScript for that purpose. So the Rust also comes in handy here. So why would you use Rust to begin with, right? Because we have this React Native app. It has the JavaScript runtime. Why not just like use JavaScript cryptography, or maybe there's cryptography in Java or Swift and Objective-C that we could use? Why even bother with Rust? And there's a couple of reasons. So first of all, Rust gives us cross-platform compatibility, right? So because our app is React Native, we have one source code for the UI, and we would also like to have one source code for all the cryptography and all the other stuff here, whistles we attach to Rust. So being able to have a single source code for this backend, as it were, of the app and the front end of the app, makes things a bit easier to reason about. The second reason is you shouldn't roll your own crypto. In this case, well, you wouldn't necessarily roll your own crypto, but the state of cryptography on higher level languages like JavaScript is not necessarily always the best. There are libraries, for especially for SecP, where you can do stuff. But you always have to think about if you're introducing a library for some cryptography, you have to think about who's the author. Is the source code secure? Is it audited? Is it vetted? Is it tested true and trusted? Or is it just something one dude wrote somewhere and maybe it's not very well maintained? Maybe there are bugs nobody knows about, and if that happens, then you might have issues down the road, and you would want to avoid that, right? So definitely don't roll your own crypto, but even if you're using third-party libraries, then you want to make sure your libraries are vetted. And in our case, both Snorkel and libsecp, they're both written in Rust. They're pure Rust libraries. Snorkel is actually written by the researcher who has been implementing this particular compression scheme for ED to 5519. And libsecp is written by our own developer, which is actually rolling our own crypto, but by now the crate is actually audited, and we use it in multiple different projects. And when it comes to party signer, we would rather use the crate that we know who the author is, and that it is maintained, and that it is vetted, and that it is audited for that reason, right? And then, of course, performance and correctness are huge reasons. If you're going to start writing in the cryptography, a lot of cryptography today still is written in C, and it's written in C because performance in cryptography matters. And if Heartbleed has taught us anything, it definitely matters more than having guarantees around your RA bounce checks and things like that, which can lead to disasters. And Rust sits in the sweet spot where we don't have to sacrifice any performance for using Rust libraries, and you also have control over the memory for things like making sure we zero the memory where some secrets are before we deallocate the memory to make sure we don't leak anything outside of the box. And finally, not specifically related to the party signer itself, but quite important for the company and the ecosystem as a whole, Rust allows us to compile all these cryptographic primitives into WebAssembly, and we can then use those in the browser, right? So we can have our main node software for the blockchain, and then tools like the party signer and browser UI stuff running completely different platforms, completely different devices, completely different languages, and they can all use the same code for the cryptography, right? So we are sure that this code, all these cryptographic primitives, they're fine, they work fine, and we don't have to worry about compatibility issues, or maybe there's some bugs in one implementation over the other. So just for coherence and for tying the whole ecosystem together and not having to repeat the work and to bring those cryptographic primitives to other platforms, Rust is excellent for that. So how does it actually work, and how do we embed Rust into React Native specifically in our case? So we have this beautiful graph over here, and we have this stack effectively with React Native UI on top. We have our cryptography in Rust on the bottom, and we want to provide bindings from the cryptography in Rust to the React Native UI. And unfortunately, the situation here is quite complicated. If you're trying to embed Rust into something like Node.js, which is also a JavaScript runtime, you can do it quite easily. There is a crate called Neon, which allows you to basically create node modules that are very easy to import into JavaScript, and they basically, bind directly to V8, which is the JavaScript engine that Node.js is using, by masquerading Rust as effectively as C, right? So it's operating directly on the memory of the V8 engine. In case of the React Native, things are a bit more complicated because React Native itself comes with a lot of assumptions about how third-party plugins should work, and also comes with the assumption that most of the third-party plugins that you might want to embed into React Native will want to use some sort of API, like location or gyroscopes or stuff like that, that are available to a developer on that platform in the native language of the platform, right? So if you're developing on Android, then that's going to be Java. If you're developing for iOS, that's going to be Swift and or Objective-C. So unfortunately, the story here is basically anyone who produces third-party plugins has to, if they want this plugin to actually work on both platforms, they need to provide bindings for both of the platforms, or code in both platforms that provide the same kind of transparent bindings into React Native. Right. The good news here is that, of course, Rust can be embedded in anything, which means you can embed Rust in both Java, and since it can masquerade as C, you can embed it into Objective-C and Swift. So the way this works is on the iOS side, you have to provide extra C headers for all functions, and those C headers can be then imported into the Swift file, which actually uses Objective-C syntax and some data types, and that then you can from the Swift file, from the Objective-C code in the Swift file in our case, you can provide bindings to the React Native using JavaScript promises, which is what React Native expects to be done. On the Android side, we use the we use the GNI crate to create the Java bindings, and from there the story is kind of similar. In Java, you have like a Java class, which with some extra annotations exports the methods and to do basically JavaScript promises in React Native. So let's have a quick look how it works. So here's a piece of code. One of the methods that we have actually in the party signer, and how we actually do the bindings. So the first thing to note is that we actually have a macro for all of our work because we don't want to repeat ourselves, and there's a lot of very, very tedious work that has to be done. But aside from the macro, there's only one piece of syntax that's actually different from regular Rust syntax, and that is this annotation top, this Java _io _party, what this is actually a Java path to a method on a class that this function is going to be mapped onto, right? Java is using periods to separate the segments of the path. This path is going to be used to create an external like C function for the API, where I don't know if the dots are allowed or not, apparently not. So The convention here is to use underscores, and then the JVM knows what to do with that, or GNI don't know what to do with that. Next thing to note is that we actually take and return, in this case, strings. So you take string slices as parameters, and our return type is a result of a string, capital S. And the reason for that is since we are working with technically 5 languages, like we have JavaScript, Java, we have Rust, we have Swift, and we have Objective-C. In order to transfer data between all those platforms, you have to find the lowest common denominator for that data type that allows arbitrary data. There is a data type in JavaScript that allows to store and manipulate array buffers with a lovely name of uint8 array. And unfortunately, the uint8 array is not really readily supported necessarily for the bindings into React Native, and even if it were, it's also necessarily might not be so easy to manipulate that from Java or from Swift. So the one type that allows to have long strings of bytes that you can use for things is string. But strings are meant for text, not for arbitrary bytes of data. So what we do here, which actually you can see, is that we use hex encoding, right? So you can encode or decode stuff into hexadecimal representation of any kind of arbitrary byte we represent in hexadecimal strings, and that's what we are using to communicate from the bindings from the Rust code to the JavaScript code. This is obviously a waste in some sense of performance. We have to do some extra work to make sure the binding works, but it is working. It is working reliably well. There's nothing that can necessarily go wrong. All of the possible encodings on all of the platforms, they all at least have the common denominator in all the ASCII signs, whether they're UTF-8 or UTF-16. So you don't have to worry about that. So all the hexadecimal symbols are represented. So we can safely encode anything into hexadecimal and move it back and forth. So this function is pretty simple. What it does is it creates a signature for a substrate account or public key. So what we do here is we receive a suri, which is basically a recovery phrase. So there's like a 12 or 24 English words packed together with maybe some extra things at the end. And from this we can recover a keeper, so we can recreate the secret key whenever we need the secret key to create a signature. So we create a keeper, so keeper, which is the secret key and the public key. We mostly just care about secret key here. And we also get the message, right? So the message the suri is plain text because it's English words using just the Latin alphabet. The message is whatever it has to be. So you have to decode the hexadecimal string into vector of bytes. You can then sign that message, and then at the end we can provide a hex encoded signature, right? So the nice thing here is that we don't have to do anything special with the error handling yet. We just return the result type, and the macro itself knows what to do with the result type on both platforms, right? So we use the config attributes in Rust inside the macro to compile different code for either the iOS target or the Android target. Now, let's look at some extra work we have to do in the different platforms. The story on Android is reasonably easy. We have to create an extra class. This class lives in a package in a special path that we've mentioned before. So all those names are the same, except the underscores have been replaced by dots. And this class already has the functions exported to them, right? So it's all my functions from the Rust have been exported as methods into this class. Now we cannot use those directly in React Native. We have to do some extra proxy. So we have this React method annotated method, as it were, which the only thing it does is actually invokes the original method, but it basically transforms this original method from synchronous call into an asynchronous call, right? So we, on top of having the seed and the message parameters, we have also the promise parameter, which is the Java wrapping around actually JavaScript promise, which can be rejected. Oh, if you know about futures in Rust, promises in JavaScript are futures. So a promise can be resolved or rejected. So we try to run our function and then resolve. If there's no errors, we resolve to the result of the function. If there's an exception thrown, which is whatever the macro did to throw an exception in GNI, then we reject with an exception. That's pretty easy. Excuse me. The story on Rust is a bit more convoluted on this, unfortunately, because there's some extra steps. So for one, you have to create a header file for our code. So there's an extra signature of how this function looks as a CFFI. In this case, this is just roughly the same thing, except the result type has been replaced by pointer to char, which is byte in C. We have 2 pointers to, again, chars for the seed and data. But there's also the first parameter, the extra first parameter, which is the error type. So there's going to be a pointer that is going to be passed into the function that the macro then inserts code for handling it, which basically is if the result from Rust unwraps to an error, then whatever is behind this pointer is going to be modified into an actual error, and then the result is going to be like an empty array or something like that, right? Then from there we go to the Swift code, which, as I mentioned before, it's using actually the Objective-C syntax, and we have an extra helper function here called handle error. And what this does is it does roughly the same thing the Java code did. So it will transform our synchronous call into an asynchronous call, right? So the Objective-C code, or the Swift Objective-C code, receives 2 extra parameters at the end, resolve and reject. So again, those are mapped to a JavaScript promise in the Java in JVM, actually in the JavaScript runtime, and yeah, so we have to create this extra empty error object, and if there's an error there, it will call the resolve, reject. If there is no error, it will call the resolve with the result. And then finally, there's another header file, this time for the Swift code, which marks the function itself as external to React Native. So there's some extra hoops, there's more files, but ultimately both the iOS story and the Java story pretty much equivalent, just using different languages. So that's really it. This basically allows us to have this, the single source for the UI and a single source for the cryptography that we then conditionally compile with different bindings to either platform, and everything works great. So some closing thoughts on this whole experiment. Rust is great for cryptography in general. So if you're thinking about either implementing cryptography from like papers or going into cryptography yourself and developing new cryptographic primitives and functions and elliptic curves or whatever else you might want, then definitely consider Rust as a tool for experimentation and implement your first implementation, if you can be Rust, because Rust gives you the control you want to have as a cryptographer over all the memory. It's a relatively high level language, so it's easy to abstract things in, and you can do that without sacrificing performance. The second advantage is obviously, as we have just shown, you can embed Rust in pretty much anything, although that can be painful at times. So yeah, actually had to do extra steps here, because our app is not. If we had 2 separate apps, one for Android, one for iOS, written in the native languages, then we would have a 1 step or 2 steps fewer in our graph. but then we would have to have the app written twice, or at least the UI for the app written twice. And if you're doing something else, if you want to embed Rust in Python or Node or Ruby or something like that, then that's, by now it's a really easy story. If you want to do it in C, then that's even easier. So Rust is great for that. A bit of a warning: if you're embedding Rust into different hardware platforms, so not necessarily x86 platforms, or even ARM necessarily, it's worth considering using a pure Rust crates. So crates that do not have themselves binding to secrets. And in crypto libraries, it's pretty common to have, there is some trusted C code that is running some cryptography, and we just provide bindings for that in Rust. For the most part, you can compile them to different targets. So you can compile your library of Rust dependencies that use C dependencies into different targets. It is possible, although you have to keep in mind that those extra embeddings tend to have extra steps for how the compilation should be done. And if you're using a cross compiler, the cross compiler can often trip on those. So using pure Rust crates is definitely advised over here. And finally, if you want to read more about this and want to go more in depth, there's a great blog post or series blog post by Marek Kotewicz from PowerTL as well, from 2017, so a bit dated by now, but still basically the same stuff about how to combine Rust and React Native, and Marek is actually the original author of the party signer. So if you want to take a deeper dive, the URL would be long, but you can quite easily find the articles by the title. So that's it for me. You can find Party, you can find our job listings at our website. You can see our newsletter for updates and events. You can find all this code that I'm talking about here. It's on our GitHub. It's all public. So github.com/partytech. You can find the party signer. You can find the React Native library we're using, or we have abstract out for the signer. So that's it. Thank you very much for listening, and have a good day.
Hey everyone, and welcome to my talk. In this talk, I'm going to talk about 3 Rust concepts, and I will try to explain them using examples from game development. If you don't know who I am, I'm Olivia. I've been part of the Rust game dev community for a couple of years now. I've made a couple of games, and I've written a short online book about making games in Rust. So with that said, let's get started. Alright, so let's take a game like Sokoban. If you're not familiar with this, it's basically a 2D map, very simple. You have a player, you can move the player with the arrow keys, and you have boxes that you need to push onto the right places. So you see here we have a couple of boxes, one of them is red, the other one is blue, and we have to push the red one onto the red spot, like this little guy is doing right now. Alright, so let's try to think how we would model a game like Sokoban using Rust concepts. So first, we might choose to model the color of the boxes and the spots as an enum. So you see there we have a box color enum with 2 variants, red and blue. We could of course have more in the future, but that's just for now. Next up, we might choose to model the player as a struct. For now, it doesn't have any state. The player doesn't need to know that much. It's all about the spots and the boxes in this game. So next up, we have the box. Very simple structure. You see it has the just the color as a member variable, and the same with the spots. All right, let's think how we might choose to represent the map itself. So remember, this is a 2D tile map. We'll probably want to store this in some data structure, maybe a 2D array. That part is not too important, so I'm kind of omitting it in this example, but we probably want to have a structure that looks like this, and we want to have these 2 functions. So the first one is for getting a box at a particular place in the map. So you see we are receiving 2 arguments, the x and y positions. These 2 are U8, it's just unsigned 8-bit integers, because we don't expect that the map to be that big. So 8 bits should be more than enough. The other thing that you will notice is that this API returns an option of a game box. So this API is really supposed to give us the box at the position if there is one, or nothing if there is no box at that position. And the same with the spot. And you might be wondering, about options, like why we chose to use the option type, and really what options are and why they are so common in Rust. So let's talk a bit about options. So as I mentioned so far, options are basically you either have something with a value or you have nothing. So you can see on the left-hand side, I just took the definition of the enum for options straight from the standard library. So it's an enum, it has two variants, some with a T or none, which basically, as I said, means you can either have something and you'll get the actual value inside that, or you could have nothing. Options are very common in Rust code. I haven't encountered them that much in other languages, but they do exist as a concept, and the concept that you might be familiar with from other languages is null. Options really are a type-safe way of dealing with nullability, of the having something versus having nothing. So while in a different language you might pass a pointer to something, and you would rely on checking if that pointer is null or not before actually using the value, if there is a value. In Rust you will use options, and you will rely on the type safety that the variants of option give you. This has a bunch of advantages, mainly the fact that the client code needs to very explicitly handle both cases, both when you have something and you have nothing, and there's no risk of really forgetting to check. You could of course still do the wrong thing. Rust will not prevent you from doing that, but it does give you an extra layer of type safety. The other thing is that it really helps us express intent when we define our function definitions. So as you saw in the previous example, we can really say, well, this API will either give you a box or it will not. And that is a very, very clear way of reading APIs and designing APIs. Lastly, on the left-hand side, you can see the option type has also some functions attached to it. I just put a couple of them, like is_some and is_none. These functions will basically tell us which variant we're in a very explicit way. So next, let's think how we might choose. Let's continue with our game implementation and think how we might choose to implement checking if the game has been won or not. So what we want to do is we want to really check if all the boxes are on the right spots. So think that we will be iterating through the map at every tile position, and we want to have a function like this, which tells us, is the box on this position already on the right spot? And we will pass the positions x, y, which are just tile positions. And this will also take in the map, because obviously the map is aware of what really lives at every position. Lastly, this will return a boolean because it will just tell us, it will return true if there is a box and there is a spot and they match correctly, and false for all other cases. All right, so first off, this implementation is very much like the first implementation that you might write in a Rust program if you are perhaps not very familiar with either options or different ways of dealing with options. So having said that, let's get started. So we'll call map_get_box, which will give us an option of a box. And you see there we're very explicitly assigning that to a variable called box option. We do the same for the spot. And then on line 5, what we do is we actually use the functions I mentioned before about checking if the option is something. So this, again, will only be true if we have both a box and a spot in this case. If we do, we move on, and then we actually unwrap the value that is inside that option. So unwrap is a function that will basically, if we have something, it will give us that something, and you can see the types there are game box and game spot, no more option. But if we don't have anything, unwrap will actually panic, and panic is an unrecoverable error in Rust. So that is interesting. Remember that for later. Next up, now that we have the actual box and the actual spot, we can simply check the colors and return the value of this expression. If the colors match, this will return true and everything is fine. If some of the options were none, either we had a box but there was no spot, or the other way around, or we didn't have anything, maybe it was just a piece of floor, we will return false. So this is a pretty good implementation. However, it feels overly verbose, and the other thing that you might feel when you first start working with options, if you're unfamiliar with them, is it might feel inconvenient. It might feel almost like you never have the right type that you want, and you have to keep unwrapping and checking and constantly trying to transform options into something a bit more useful. And that is a very natural thing to do. The good news is there are other constructs that Rust provides that can help you work with options better. And working with options is a very important part of writing idiomatic Rust and being able to feel like you're using Rust to the fullest extent. So moving on, let's think of what a different implementation might look like for the same function. So we could use something called if-let. And again, I have not seen this in other languages much. I think Swift is the only one that has it. But it goes like this. We're going to call map-get-box with the x and y position. And then we're going to say, if there is something in that box, assign it to a variable called the box. This is basically a shorthand way of writing what we wrote in the previous option, but you can see it's less verbose. We're basically just saying, if we have something in this box, assign it to this variable, return true from this condition, and move on. So if we go to the next line, you'll see that we can do the same for the spot. And finally, now that we have both a box and a spot, we will check the colors and we will return that. Similarly, if some of the options, if one of the options was none, the if-let condition will actually return false. So we will jump straight to line 7. Cool. You might be thinking, well, this is already less verbose, which I completely agree with. It's also more idiomatic. We're basically using a language construct to deal with the options, and the if-let will do the checking of, do we have something, do we have nothing, and we'll basically assign the something to a variable without us having to check is none, is some, and do the unwrapping ourselves. And this is important because in the previous example, we could very easily forget to check is some before we actually unwrap the option. And what that means is that we could be unwrapping an option that is actually none. And that is a problem because we will get a panic. We will not be able to recover from that error. So this code is slightly better from that point of view because it gives us a bit of additional safety. The only inconvenience is the nesting, but I don't think that's such a big problem, especially when we only have 2 options. Next up, let's think of a different way that we might be able to write this code. So the other thing that we could use is we could use a match construct. Match, again, exists in other languages. It's a bit like a switch statement, but a little bit more elaborate and more powerful. You'll be able to do a lot more things with a match than we'll be able to do with switch in other languages. We won't see their full power here because this is a very simple example, but you should know that. So again, we're calling map-get-box, we're calling map-get-spot. Remember those return options. And then we'll basically be able to say, well, if the pattern that we've put in the match is some with a box and some with a spot, then do this. And we will basically check the colors of the spot and the boxes. If not, if the pattern is anything else, so that could be we don't have a box, or we don't have a box or a spot, then we'll go into line 6 and we'll basically return false. As I mentioned, match gives us the ability to do more powerful things. We haven't seen the full power of it because this is a very simple example, but I think you get the point. Arguably, this is a little bit harder to read. We have some slight complications in the syntax because we're actually using a tuple to be able to match on both things. Otherwise, we would have to match on each option individually, which we could also do, but that would be a little bit longer. Hopefully that made sense. That was 3 different concepts. We talked about options, we talked about if-let, and we talked about matches. Hopefully that is enough to get you interested in these concepts if you were not familiar with them before, or if you were, hopefully it gives you the appetite to dig a little bit deeper and understand them a bit deeper in terms of both how they are implemented and how they help us write more idiomatic Rust. Finally, if this sparked your interest in making a game in Rust or getting started with Rust at all, I have a short online book that will teach you how to make a game like Sogoban. Exactly what I showed you in the first GIF. You'll basically be able to build that at the end of this book. It's very short. I highly recommend that you try it out. And finally, I put some links to my social media profiles and a link to the playground that includes the code in this talk. Thank you very much.
Good evening, good afternoon, or for me, good morning. It's just before 5 a.m. I am super excited about this talk. I've actually seen a couple of the other speakers this morning, and I've been really, really impressed and really excited that there are hundreds of people participating. Now, if you are on Twitch, which I assume that you are, if you're listening, do make use of the comment section, and I am monitoring them sporadically. So as I go through, I'm going to try and feedback, and do use the Discord links in the panels below, because we can continue the conversation afterwards. Okay, so where should we start? How about the beginning? What we'll actually do, though, is start with this very small warning. And that is that this talk is going to be slightly controversial. Hopefully not very controversial. So our objective this morning is slightly different than most Rust talks. And what I'm actually going to try and do is identify the very smallest subset of Rust that actually enables someone to write software that, you know, they really like, and they can talk about it with their friends and their colleagues. And by the way, feel free, as again, I want to reiterate, you do the chat, and if you're watching on the recording after this, you can send me a tweet, or look in the description below, and I'm sure that there'll be a link into the Discord server, and we can continue on the conversation. Now, for the people that really don't like long talks, here is the 60-second version for you. First of all, the biggest thing is that actually, while you're learning, it is completely okay, 100% okay, to write unidiomatic Rust. You might, and maybe even slow, or possibly even memory, you know, we don't have to go for perfection at the start. While you're learning, it's okay to learn. And here are some guidelines. You know, some people get really concerned about borrowing. Am I using clone too much? Am I using for loops rather than higher order programming? I don't know what I'm dealing with, like result. Sometimes I'm using memory allocations. So like all of this extra good stuff can wait. And in fact, I've got like a very personal opinion here. So like the flames are out. You should try and focus on understanding the trait system before lifetimes ownership and borrowing. Lifetimes ownership and borrowing are quite alien to programmers who have come to Rust from another domain, and that isn't necessary to start, actually. You will need to learn it eventually, but as we start, no, you won't. Okay, right. So we've done the warning. We've got through our objective for the talk. We've got our invitation for comments already in place. And the 60-second version, so what's left? I'm going to spend a little bit of time talking about my own personal journey with Rust language. And I want to define a little bit more precisely what I mean by learning curve, because I think it's a term that people use, but actually it's poorly defined. I want to have a go at defining a minimal subset of Rust that's productive. And I also have some tips, because as I was drafting this up, I realized that, you know, if you're going to watch a Rust talk, and you've probably either done Java or C# or JavaScript or Python, there are idioms inside the Rust community that are different than the rest of the world. And that's almost like a cultural shock rather than a technical shock. And I've also added some extra content at the end in case I need it. So, story time. For me, actually, learning Rust was really, really hard. Things would be great until they were not great. And allow me to provide you with two examples. So here I am, I'm happily adding numbers, and that's working fine. I've got A and B, there's two variables, I'm adding them together. And then in the second part of I'm just doing the same thing again. You know, this is perfectly natural for someone who spent like nearly a decade in Python. And then I provide a very, very similar set of code. A string, I've got the string thing, once upon a time, I have my little story, and I join them together with concatenation, and then I use it again somewhere else. And actually, the second version will fail to compile. But if and I was really confused because like here's the addition, and here's concatenation. That like one is correct somehow, and one is not correct, and that for me was difficult. It turns out that Rust will restrict your ability to reuse variables, and it does that for very good reasons, because systems programmers, and Rust, in the broadest sense, as a systems programming language, will prevent you or attempt to prevent you from misusing data. And in particular, this type of use is frowned upon by the Rust compiler. As we'll see, though, the Rust compiler is not your enemy. The Rust compiler is your friend. Okay, so by the way, I just noticed that inside the chat, we have got a shout out to the Rust in Action book, and also there's a question: what is the difference between Rust in Motion and Rust in Action? It's a perfectly reasonable question. So Rust in Motion is a video series, and Rust in Action is a book. And if you want both, there's actually a bundle. So if you go into manning.com, and then you scroll down on the right, there's a section for sort of bundles. You can buy them together as a pack, and it saves you a lot of money that way. Okay, so back to the talk. What do we mean by the learning curve? Okay, so here is our mental model of what the learning curve might be. We sort of start at 0, and after some time, we progress to 100%, right? So this is kind of our mental idea of how things work. There are a lot of flaws with this model. You can't just pour knowledge into a brain. Like, brains don't work that way. But we're gonna, maybe we're gonna try. Okay, so allow me to provide three different stories. So this one is someone who's actually just not learning, and she has this mental model that she's never going to get there. And maybe there's probably two reasons why this, but in one case, it's too easy. Like the material just isn't relevant to her, so she's just not engaging with it. There's another potential. So we notice we start at above 0, and that's because you have some prior knowledge. So that's one person that we want to talk to with this talk. So what's another strategy? Well, what's another? Well, we can't see it because actually it's underneath the overlay, which I don't control. But I've actually added the y-axis, so it's a negative, and then we start down below. And this is your prior knowledge actually interfering with learning something new. And so this is kind of the problem, or one problem that programmers feel when they try to learn a new programming language. It doesn't matter if it's Rust. It might be you're trying to learn Java and you've only used JavaScript, and suddenly you try to write JavaScript in Java. And likewise, many people try to write Java code in Rust and find it really difficult because they've got some historical knowledge that doesn't map into the new domain. Okay, and this is actually, here's another curve. Now, this is someone who's tried and has found the learning curve very, very hard. And they are struggling. So they project out and they say, well, look, I can probably maybe make it, but it's much too hard for me. Like there's too many new concepts here. I've got a lot of domain knowledge. We know that because we don't start at 0. We start above 0. And that is the person. Now I'll just go back there. This is the person who I most want to talk to about a different approach for learning the language. By the way, I just saw the comment about Fortran 47. Sorry, Fortran 77, not 47. To C++, and then Python, and now C#. Right. So I think it's important to remember that we don't stick with our tribe, like we do learn new technologies as we go. And I think that Rust is a very strong contender for the next language that you learn. It's definitely made me a better programmer. Right. So the heart of the talk, minimal productive Rust. Again, I apologize. I'm going to have a quick drink because it's just after 5 a.m. now. So, and I'm flying through the talk. I've nearly through half of my slides. So we'll see how we get there. I mean, how we go. Maybe I can just spend some time on stream chatting to people and answering questions. So we need to deal with text. What's our minimum viable talk? We need numbers. Like we can't do much with a programming language that doesn't have numbers. I feel that iteration is very, very important or kind of critical to Rust's approach. Pattern matching, as Olivia mentioned in the previous talk, is very, very powerful. Option and result. Now, I don't know if this is right, and I really want your feedback on this, but I think that you can do most of what you want to achieve with Rust with just learning this. Now, this is this is my controversial statement because there are a couple of things that are prerequisites that are hidden in here. In order to know about iteration, we need to know about containers. So that kind of comes naturally. So we need at least vector and pattern matching. Well, that requires you to know a little bit about enumerations or enums. Option and result maybe kind of also imply some knowledge about enums and to a lesser extent knowledge about generics. Now, we'll see how far we go. Okay, so just to make it very, very explicit, here is some attractive, easy to use, highly performant code that tests whether or not there is a positive number inside a container. In this case, it's a vector of 3 elements. Now, if you are new to Rust, I would like, and I'm hopeful that this will, we've got some problems. First, the one question is, like, why do I need an iter method? Like, if I'm from Python, that doesn't make any sense to me. So what's happening here is that vectors need to return a type that knows how to iterate over the vector. And so that's what iter does for you. And that's a kind of weird concept for maybe someone who's come from a dynamic language, that you can't actually iterate over, like a vector wouldn't know how to iterate over itself. But if you're from C++, it makes perfect sense, right? So, but here's the scary thing. Actually, we've got this any method, and now any over an iterator takes a closure that takes a reference to each element, and then applies some predicate to that element. Now, immediately, I'm like, whoa. Okay, so there's quite a lot to take in there. Okay, first we need to know about closures. We need to know about references, and then we need to know predicates. And like functional, so we need to know about lambda. So we mentioned closures as well. And I feel that while you're beginning, my controversial statement is that that's too many concepts to pack into one line of code. And I really, really want your feedback on this, because I have an ugly replacement that I actually want to recommend to you instead. So here's my ugly replacement. So this feels probably something that's much more traditional. So we start and end the same. So we start with our A. Our A is a container of 3 elements, and we have this assert thing. Assert is a macro that will test that will basically crash the program if there is a false value there. And won't compile if there's not a Boolean. So you actually already have type safety baked into the assertion system. So now this is a Boolean value. We have to declare it with mute. So and that declares that this this variable, at least one positive, is mutable, or at least it can change. So over the course of the program, it could have multiple values. Now, this is kind of unrolled or unpacked. It's much, much longer than the other one. we have this iter thing remains. In fact, there is a way to get rid of it, but so it remains for now. And we've got the star operator. It's actually the inverse of the the address operator. But so we still have one confusing thing if you're from JavaScript. If it's greater than 1, we set it to positive, at least when it's positive is true, and then we break out of the loop. So this is something that is much more familiar with only 1 or 2 added concepts. And so my thinking is that for the moment, I want to give you permission to write ugly code. Now, I would prefer it if like all of Rust wrote gorgeous, gorgeous code. That's there are some performance benefits as well for using quite a declarative functional style. The compiler is able to optimize it really aggressively. But right now, you don't need it. Your programs will be fast enough. And the code will be so the code will be fast enough, and you'll be able to understand it, which is important. Okay, right. So now I've given you my introduction to Rust. I want to try and show you one of its superpowers. And that's this from stir method, which enables us to construct a type, in this case point, from an arbitrary string. So we kind of can create these little mini baby parsers inside our types, inside our methods, and this is actually a supported part of the standard library, and you can implement it for just relax. It's okay. We'll get through it. For arbitrary types. So in this case, we let's walk through. In order to, and the reason why I'm showing you this is I want to demonstrate where you can get to, not where you start. And I want to kind of give you the just a little bit of excitement about how powerful this language is. Right. So we've got std, which is standard, stir, strings, and string slices, and from stir is a method which is an interface, or in the Rust world we call it a trait. So up the top we've got a trait, and this thing here is an error type, which is actually comes in quite handy very shortly. We annotate our type with two derive macros, and this says, "Dear compiler, could you please implement this code on my behalf?" So I would like, dear compiler, please implement debug and partial equality. So debug enables a string representation to be printed. It actually works in conjunction with the printline macro that we will see very, very shortly. Partial equality is a trait that enables 2 types to use the double equals operator. And the reason why it's partial equality and not just equality is that floating point numbers have this particular like fishhook in there. And the fishhook for floating point numbers is that if you have a not a number value, or 2 of them, and even if they're bit for bit identical, so they're exactly the same value, they by design of the standard, the not a number values never compare as equal. In order to accommodate that inside Rust type system, the standard type is partial equality. Right. Okay, let's go on with our code. We have 2 integers that are of width 32 bits. Now, if you have not used Rust and you have not used the systems programming language, and you don't know why there's a 32 there, I recommend reading my book, actually. That will tell you. We describe a lot about why numbers have a fixed width and what those widths are. Okay. So this is an implementation of that trait. It returns a type, but this is the kind of, this is the real magic. Now, this is an example from the standard library, and the reason, and it's actually in there right now, and the reason why I brought it out is it uses a lot of things which I think are too hard to start with. So, and like in individual pieces, they're not too difficult, but like seen like this, it's just like, is this really a simple example? Like, I think this introduces a barrier to entry, but also it's a difficult question for the Rust authors as to like the examples in the standard library. Are they for experienced Rust programmers, or are they for junior Rust programmers? So what does trim matches do? Trim matches again takes a closure, which takes a single element and then applies a predicate, and trim will clip it off the end. So what it's doing is saying, I'm going to strip these two brackets, one on the left and one on the right, or braces. I'm never sure on the American term. Just say round brackets. We split it into two, so we can see here that we've got a comma in the input, and that will be split into a vector of 2 lengths. And this collect thing is kind of the reverse of the iter method that we saw earlier. So iter will take a vector and turn it into an iterator, and collect will take an iterator and like suck that all up, vacuum it all together with and create a vector. And so we get out is this vec ampersand stir thing. Now, it's unfortunate, and we'll discuss why very shortly. It is unfortunate that Rust needs to introduce this ampersand term like syntax so early on. It's basically fundamental, it's essential complexity rather than accidental complexity. Right, so then we get this kind of crazy syntax over here, and there's a lot going on. So coords square brackets 0 is this one over here. So it's actually this one up the top. Now, the parse method takes a type and attempts to parse the string as that type. And you'll notice that there's a very nice affinity between I32 up here and the I32 back below. And so what we now have is, but what I'm kind of concerned about is we have a concept that's very unique to Rust, which I enjoy. It's called turbofish, so you can look that up. Turbofish is kind of a way to provide type annotations inline, or like very, very closely to particular methods. It's actually, in some sense, an argument to the method, but it doesn't exist inside the parameter list itself. And then I've got this question mark operator as well. So that's another new concept. And I just feel like this example, while correct and very, very fast and good, like maybe if I was learning Rust today, I don't know if I would be able to read it. So actually, I'm going through all the code. There we go. And right at the end, I get to okay. What on earth is okay? Okay relates very, very tightly to result. So remember earlier I said one of the things you should learn is result, and I will leave that as an exercise to the reader for now. Okay, so we've actually covered a lot of Rust already, but I want to show you how far you can get with a couple of so the reason why. I was going to justify why I had that big long example there, but I think we'll just stick with our we'll just stick with the present. Okay, so with function main. So every Rust, all Rust binaries have a main method, and the print line. Oh, by the way, I must say that I am super, super excited and really, really glad that people are answering each other's questions on the chat. I'm doing a terrible job monitoring them. So thank you very much for asking, and also thank you very much for responding. Again, sign up, use the link in the panel underneath the talk if you're on Twitch or on your mobile, scroll up a bit and find the Discord link, because we can continue on the discussion. So this is where we start. This is we print hello world to the screen. That's fine. That's great. We've done that everywhere. So what are some new concepts? We've got this FN keyword, which looks kind of sort of familiar, but also no one else uses FN. We can see there that Rust looks like expressions we've got the semicolon, which is fine. That's pretty standard. Double quotes are required for string literals. This is actually hidden. If you have attempted to use single quotes in here, you'll receive a compile error for very valid reasons, which I will explain later in the talk. And related, we have like a whole ecosystem of text types, but that is hidden knowledge for now. Okay, so now we want to add templates to our print string. And print line, and now we have a variable world. So we can actually ask the print line macro. We'll kind of interrogate this string literal over here, and we'll look and say, okay, well, there are these two braces here, and we'll just fill that in with whatever we want, whatever we receive as the first argument. Cool thing about Rust is that if you put in the wrong number of arguments, even to these macros, the program will refuse to compile. Or if you put in something that doesn't implement debug, actually, just this one is syntactic sugar or a marker for the display trait rather than the debug trait. But yeah, so that's good. Sorry, there was a thought there, I'm sure. Now, okay, we're adding some complexity. We want to replace we want to parameterize our function or our method. So we've got variables. They look quite standard, although let like, really? So Rust it looks on the surface a lot like C++. It's used in a domain of or at least it started in an area where C++ is very dominant. But a lot of the strategies or a lot of the below the surface features come from the ML family of languages. So that's OCaml and Haskell. And they are much closer to mathematics. And so let instead of var, for example, kind of harks back to the way that mathematicians speak. We encounter immutability, although it's hidden. In fact, so it's the right side of the bracket, so that's not close. There's an unmatched parens there. That's useful. Now we will get snagged on this later, actually, or at least new programmers can get caught that you can't modify user unless you ask Rust to allow you to do so. So now we're going to add a little bit more complexity. We've got our user variable, but actually we still have a fixed string. So to make it a little bit easier, I'm going to introduce environment variables as the way we go forward to start. Oh, that's a little bit too big. We'll push through. And rather than command line arguments to start. So I need to, just looking at this kind of core of Rust, like how far can we go? I got an import, and so that's okay. I've got a new concept in here, this use thing. That seems okay. That's understandable. Let again. Now, unfortunately, for this code, I need to actually call a toString method, and as a person who might be new to Rust, that feels like a tautology. Like it might be completely unnecessary. Like, isn't world already a string? In Rust's eyes, no, it's not. And it's actually a specific type of internal representation that is not equivalent to a string type in Rust. And we'll just kind of keep that one there. Okay, so I told you earlier that it's really important when you're learning Rust to understand result and option. So if I ask for the user environment variable, I will get back an option. An option is a type which enables you to say, to encode the possibility that there is nothing there. So, you know, if you're running Linux like I am, the user environment variable we set to the user of the that you're currently logged in as, so that in my case is probably Tim, but there might not be a user environment variable if you're running inside a container, for example, and then there might be this none value. So we introduce a whole set of methods called unwrap. So you could think of result and option as wrapping a value, and unwrap basically unpacks that, and there's some associated methods. In this case, we've got unwrap or, and we want to go back to our default. Invat, by the way, will always return you a string, and so, or well, an option of string, and so that's why our default variable also needs to be a string. Okay, so we're trying to introduce concepts slowly and iteratively. Right, and so I'm just thinking of the kind of things that might look a bit weird to people who are new to Rust, like unwrap, really? Like I still, in fact, there is a big long, if you are interested in the internals of Rust, used to, actually, we won't, there was a bit of a flame war about the term unwrap, actually, very early on, before pre 1.0. Sadly, getting input from like a command line argument turns out, oh, actually, no, this one's standard in. Okay, this isn't command line. So this would be this is madness, and I apologize for that. It's actually, though, but let's get through it. First we need to initialize a buffer, which will take in the input from standard in, and basically gets populated with the values that are provided by standard in. It's very, very common in Rustland to chain methods together. So I've got trim here, and trims white space from the left and from the beginning and the end. And then again, we use this toString method to, actually, I think that's redundant. Previous version of this code used something slightly different, although I'm now second guessing myself. That's a bit strange. I wonder if trim doesn't return a string, trim might return an iterator that needs to be converted to a string, because of the way that so I want to confirm why there's a toString method there, but here's, and I'll kind of carry on through this example. What is in our minimum viable Rust? We've introduced the match keyword. So in this case, we're matching on a number. So buffer has a len method. So the string type has a len method, which will return the length of the string. In which case, if it's empty, we provide a default, and otherwise we introduce an ampersand. We'll say that user becomes a reference to the string, and we don't right. So let me kind of introduce some new Rust. So many modules introduce a result type themselves, which kind of is familiar, but can be a source of problems. So this is one area to be be comfortable with as you kind of grow, or at least forgive yourself for getting frustrated. That's what I'm trying to say. The string method is the string type has a new constructor, which is a common pattern. This isn't imposed by Rust at all. It is imposed. It's just a convention that a new method returns a new object. And I think, and this is the first use in my talk of the match keyword. Match is kind of like select, but actually much better. So unlike select, for example, it will exhaustively test every single possibility in the type system. In my case, so basically everything from the negative infinity to positive infinity, like constrained by the amount of the number of numbers that a given type can represent. I can also use an underscore if I want to be able to say anything else. And by the way, len cannot represent negative numbers, and so there's no reason to think that you might get a length of -17. Okay. We've introduced a little bit of complexity here because this result, almost everything in IO land can fail, and so we need to return a result ourselves. This nested, these two braces here look like maybe like a tuple or a list or some kind. In some sense it is. It's an empty list. It means this also, it's called unit, and this makes sense to any mathematicians, but to any people new to Rust, it kind of just looks a bit strange. So what we're doing is okay, our result is actually a wrapping unit in this case. So these two braces, or these two parentheses right in the middle, actually represent an empty type. Okay. Oh, I've gone through all of that. Okay. Now, I don't mean to pick on actics, but this is one of, like, this again is the beautiful code that is really succinct, but also is very intimidating, I think, for newcomers. And one thing that I want to tell you as someone who's learning the language, that you shouldn't expect yourself to be able to know this. Like, don't expect to know what everything means here. By the way, so this get thing, this annotation to index, or this annotation index main to our main function, is provided by Actix itself. It doesn't exist within Rust. Async is different. We've got some new types in here. We wrap string or with this path thing. We've got to implement a trait. So we need to return something that implements responder. But if you don't know what responder means, that's not provided in the standard library. Now, I think that it is important for you to be very, very tolerant of yourself, and like say it's okay to get frustrated, because there's a lot of complexity packed into very, very few lines in a lot of these introductory examples. I'm just going to spend 2 seconds to check the chat. Now, there's one which I think is important, which is the parents just a type. So that's here, and yeah, so it's this unit type thing. Not very well explained, unfortunately. Unit is like you can think of the Boolean type as having 2 values, true and false. The unit type is strange because it only has 1 value. It is just unit, and like you can think of larger types like Booleans having multiple values either, but this actually, the domain of unit is unit, and so it's kind of strange from like an abstract point of view. Oh, I'm super excited that people are just like having a good conversation. Allow me to. I can't see lots and lots of direct questions to the talk, so I'm just going to push forward and maybe provide some more advice for people learning. So I've hopefully provided a little bit of motivation as to why I think that you can, why we can kind of shrink 100% from the learning curve. You don't need to learn all of Rust before you start programming in Rust. As a Rust philosophy, avoiding stringly typed data is very, very strong. Do take the time to understand pattern matching. Matching is very powerful and is subtly powerful as well. I believe that Rust error handling is again subtle and probably quite difficult. It's not an exception-based language. There are no exceptions in Rust, and understanding what result is and what option are is really important. So on the surface, Rust looks like C++, but in many respects, it's closer to ML. And this will maybe provide you with a little bit of an inclination as to why some of your mental model doesn't map very well across into Rust. So I should also say that, just to kind of like the throwaway comment that I like to use is that Rust is the language where Java programmers and Haskell programmers can kind of get along. Like there's enough similarities for both worlds to actually be able to talk friendly to each other. So one thing I want to reiterate is that your compiler is actually a coach. It's not the enemy, it's your friend. And another thing is that when you're building abstractions, Rust will fight very hard to avoid oversimplification. And even when that makes it more difficult for new learners. So allow me to flesh those out. So if you are new to Rust, it's very, very common to return Booleans. Oh, actually, this is not what I intended to mean. Sorry. Right, okay. Sorry, I've just got my slides a little bit muddled up. Okay. We're kind of pushed through. So you can imagine that instead of bool here, I might want to return something that's like, actually, if we just avoid stringly typed data for now and and put in don't use Booleans, just to kind of get you through the culture shock, it's very common for Rust programmers to create little types. So the reason why you'll want to do this instead of just returning a Boolean is that you create self-describing code later on, because you're always going to have, you'll receive strong, weak password strength. It's all going to be together. And so cognitively, you reduce the load in the rest of the program. Because if you have received a Boolean from this function, there's no difference really. Like you need to mentally remember where the Boolean comes from later on. I do want to speak just very, very briefly about stringly typed data. You saw earlier in a couple of examples where we took strings, and in the case we remember had that point, and we were able to implement a trait, the from stir method, to convert that very, very quickly into a concrete type. That is idiomatic Rust. And it allows us to play very along. And if you take any input from a user, do take the time to actually get it into a concrete type, and that will allow your type system to actually support you. I really like pattern matching, and unfortunately, again, like these things with writing slides, you immediately see the problem. So here's a command line. This thing here is a bit of a mess, but I'll talk us through. We've got env, which is our environment that the program sits in, has an args function, which returns the command, an iterator over the command line arguments. So then we want the first command line argument. In fact, if we ask for 0 there, we'll get the name of the program itself, but env1 will provide us with the first argument provided. If you don't give us one, we will error out and say that I need you to provide me a guess. So this is just the guessing game thing. I don't know if anyone programmed in BASIC, but I definitely did. And every introduction to BASIC provided you with a guessing game example. Now, this is very similar to unwrap as before, but instead of just blowing up and crashing, we have this error message as well. So inside guess raw is a string. We want to convert that to an actual integer. So again, I can make use of this parse method and annotate parse. So it's string that has the method, and then we need to add a type with turbofish, which kind of gives the Rust compiler enough information to be able to convert guess raw into an integer. Right. And so pattern matching can provide you with a lot of simplicity as someone who's reading the code. I just want to introduce some syntax that isn't very commonly discussed, which is the ability, in fact, to have these guard clauses on the side. So X, X will match anything and also assign a variable to X within the context of this line. So X is defined here and made use of. At runtime, Rust will check. Now, because we're using these runtime guard clauses, we also need an OK, and we need an OK wildcard, because the Rust compiler will refuse to compile the code if you leave this line out, because at compile time, it wants to guarantee that every single possibility has been taken care of. Now, if you provided some input which was not a number, parse will actually return an error. And in fact, it will be the error type that we saw earlier, which is the parse int error. And our error message to the user will be like, you should use a number. This is silly. What are you doing? And so then we go at it. And there's a lot of simplicity involved in pattern matching. I think it's a really, really effective way to write your code. Match will also work on tuples, which is a type, and is extremely good at making truth tables very, very readable. Again, just as a very small plug, if you read Rust in Action, you'll see this often used. Okay, so there are three types of ways to deal with errors in Rust. Sadly, in some sense, or thankfully in another sense, there are no exceptions in Rust. What we do have is panicking. So panicking is your program crashing, and your program will happily crash if there's an unrecoverable error. If you attempt to divide by 0, actually divide by 0 might be slightly different. If you can invoke a panic or a crash with a panic macro, but allow me to talk about result and option again. We return result when we have a recoverable error. If there's something that can be encoded inside your source code as a way of dealing with a problem, we can use result. And so, for example, with all of the I/O methods and functions, almost every one returns a result because the file system might be broken. The hard disk may no longer be there when the method is called. There could be some corruption on the disk, and so there's no guarantee. Use option if you want to represent the possibility that there is a missing value. It's kind of a subtle distinction between result and option that I found really complicated when I was learning Rust, because sometimes you feel like you want an option, but sometimes you want a result. And one way to think about option is that if you are, say, interacting with a hash map or a container, a hash map is really good. Like you say you want the Rust in motion value from a set, because you've got a you've got a set of really great Rust resources. And so Carol and Jack's video course is a really, really good one. And then you that might not be in your set at the moment, and so you'll actually, the method will return an option. Okay, so again, we've talked about what Rust looks like on the surface, and we use lots of angle brackets, and it looks like it's very, very heavyweight in some sense, and like very serious. Unless I found it kind of intimidating as someone who's just, before Rust, I programmed in Python and JavaScript. So I would like to stress that Rust is more about performance. It's actually much more about allowing you to build good software that you can be really, really proud with, that's robust and strong and fast and lightweight. And so, and the other thing that I really want to stress about Rust is that it's not just the syntax, it's not just the compiler, it's the community. And being involved with a community whose mission right in the front is empowering everyone is really useful, especially for me. Like, you get so much on the technology side. Like, we got high level code and excellent type system, pattern matching, a whole bunch of really, really useful features, but we also have this like kind of super boost pack. Like I'm trying to think of the right example, the right analogy of the community. Right. So our other lesson is that the compiler is a coach. Now, this will not compile. Can you spot the error? Now, I couldn't when I started. And I'm just going to wait for 10 seconds. There'll be a bit of lag for the chat to kind of carry on. But where is the problem here? All this code is supposed to do is print a equals 10. It will refuse to compile. And the problem is this is line 4. What turned me on to Rust? Oh, look, there we got double equals. There we go. Yay! Everyone is much better. You're all better programmers than me. Now, I have done this in Python too many times to admit. Used assignment instead of equality testing. This doesn't exist in Rust. That problem never happens because the compiler will refuse to put, and knows that an assignment should not exist inside the context of an if block. The type system is really, really good. And it is, yeah, that's why, yeah, the Yoda comparison thing, like, because we can invoke errors in other languages, but Rust, it's baked in. Now, here's something, again, that's a little bit controversial, but I kind of want to justify it. Like, there's someone, again, like I started programming in Python 2. So I had this kind of distinction between a Unicode object and a string, and that I kind of found irritating. Now that had been unified in Python 3, and we've got bytes and strings. But in Rust, you've got every string type. And the reason is actually a little bit more subtle than, like, this is not done for fun. It's done because reality is complex. And oversimplifying these distinctions means that we lose control. So Rust will always provide the ability for the programmer to get as close to the metal as possible, which means that it will there'll always be a way for you to basically manipulate individual bits inside any given type. Like, you can find a way to do that. And I'll just talk very quickly about what the difference is about all of these types, because it's really, really crazy if you're new. Okay, so ampersand string is a reference to a sequence of bytes. In fact, but with the, and so whenever you see an ampersand, that you could think, I think of ampersand, it looks like it's address. I think it should probably have been the @ sign, but whatever. That's the syntax that was inherited from C, so that's the syntax that we're using. So now a string literal is often, you'll see it annotated with a lifetime which is static. Now that doesn't make any sense either to you if someone who's new, and the reason is actually kind of obscure. The lifetime should have been like forever or like global or something that represents the lifetime, but actually the static lifetime is a representation for the location in memory that the string or the byte sequence is held. Now there is a stack and a heap and other bits of memory, which again is important and useful for some subset of programmers, but for beginners it is not. And the difference between this thing, which is a slice of bytes, and stir, is that stir is guaranteed to be UTF-8 encoded. So is string. Now string, for people who are C++ programmers and are curious about Rust, string is a heap allocated string that, and so is dynamically allocated at runtime. Whereas stir is just a slice of bytes that may, or like we don't actually know where it lives. So string is more flexible, but also it incurs possibly it incurs a few very, very minor, well, we can copy data around unnecessarily. And so if you are a if you are a Rust programmer and you're a professional Rust coder today, you'll probably prefer to use stir whenever you can because it will avoid allocations. Now, there is also a type specifically reserved just for an individual character. This represents the entire range of Unicode. Everything that can be represented in Unicode can be represented within the char type in Rust. And that's because char actually maps to, there's technical reasons as to how that happens, but it's no longer a single value, it's a single byte. There are 4 bytes which are used to do that mapping. Now, the difference between a slice of bytes, which is a slice of U8, and a vector of U8s is the same distinction between these two types here, except there's no guarantee of a UTF-8 when you're just dealing with raw bytes. Now, this kind of is subtle because often, I say often, if you have data over the network, you might not it will only come in as a stream of bytes. And so all you might get is something like this. You'll need to do a manual step to convert it or kind of promote it to string. We've got a couple of others. So C-string is analogous to, well, it's internal representation matches string. OS string will match whatever the platform is using. So Windows, I think, uses UTF-16, whereas in Linux, there's a whole bunch. File system paths are unique, and that's why all of our strings are different. So I'm just hitting time. So I want to introduce a little bit of kind of a reason why you should move forward with Rust. You're able to, once you get a handle on like some of this type system stuff, you'll be able to know exactly, you'll be able to accept like stir, string, maybe path, or because anything that can be converted into a string will be able to have its password length checked and to check whether or not it's at least five characters long. And I just want to finish with this with these thoughts. You control where the finish line is. And I want to support every person watching this stream to learn how to program in Rust. If this is something that you're curious about, ping me on Twitter, hit me up in the Discord chat. I run a Discord server and a Twitch channel myself, and the reason why I'm writing a technical book is to educate. And so if I can support you, I want to do so. So please feel free to ask me any questions at any stage. Thanks very much.
Well, hello, everyone. I think we are live. Greetings, all my fellow Rustaceans from around the world. Thank you so much for having me here today. When I work with someone who is just learning Rust, they sometimes question whether the Rust borrow checker is their friend or their foe. If you take a look at the Rust subreddit on Reddit, you will see posts like this. Newbie question regarding the borrow checker. Help fighting the borrow checker. And a beginner question, does it ever get easier fighting with the borrow checker? I see these a lot when people are just starting with Rust. However, as I watch people get more experience with the language, they tend to come around to the borrow checker and realize what it protects them from doing. So in answer to the question, is the borrow checker a friend or a foe? I say the borrow checker will become your friend through experience. And along with gaining experience with it, it's also very helpful to understand how it works and why it does the things it does. We're going to dive deep into that, but before we do, let's briefly cover who I am. I'm Nell Shamrell-Harrington. I am a Rust engineer. I was most recently at Mozilla. I'm also the lead editor of This Week in Rust and host of the This Week in Rust podcast on the Rustaceans Station. If you want to get in touch with me, Twitter honestly is the best way, so feel free to tweet me at Nell Shamrell. And I'm so glad to be here with you today. And to set some expectations, we will first do a bit of background on the Rust compiler in order to put the borrow checker in context. Then we will do that deep dive into the borrow checker and how it works. So let's go ahead and start with an overview of the Rust compiler. And to do that, let's look at a piece of Rust code. This Rust function declares a vector composed of the integers 1, 2, 3, 4, and 5. And after it declares this vector, it then uses a for loop to iterate through each integer in the vector and print it out on a new line. Many of us do this kind of exercise when we're first getting started with Rust. And once we have that in our editor and have it saved, we can go ahead and run it using cargo run. And as expected, we will see the numbers 1 through 5 printed out on the screen. Now, this seems pretty simple. Cargo builds and runs this piece of code for us. But there is a lot that happens underneath the surface in the compiler where Cargo is building it. There are 5 general stages to compiling a piece of code. It starts with a lexical analysis of the code, then parsing of the code, followed by semantic analysis of the code. This is where the borrow checker will come in. Optimization of the code. And finally, code generation, where the compiler creates the executable binary of our code. When we look at the stages laid out like this, it might seem like they will run linearly. And in some compilers, they do. However, if you've delved at all into the Rust compiler internals, you might be thinking, wait a minute, isn't the Rust compiler at least partially query-based rather than linear-based? And the answer to this question is yes, but that is out of the scope of this particular talk. For the sake of clarity, I'll speak to the internals of the compiler as if they were functioning linearly. However, if you want to delve more into how the Rust compiler is query-based and what that means, check out the guide to Rust C development for more information. This guide has been a big help to me as I've learned to hack on the Rust compiler myself. Going back to these stages of compilation, let's start with the first one here, lexical analysis. At this stage, a program within the compiler called Elixir takes the raw Rust source code that we wrote, this is called a lexeme in this context, and analyzes it, and then splits the code into tokens to make it easier for the compiler to parse. And this is about all there is to lexical analysis in the Rust compiler. After this stage, we get to parsing, the next stage of compilation. And in this stage, a program within the compiler called, conveniently, a parser, analyzes the tokens generated by the lexer and translates them into an abstract syntax tree, or AST. Having the tokens in this data structure makes it much quicker and easier for the compiler to do the rest of its work. And at this stage, before it moves on to that next stage of compilation, the Rust compiler in particular will take that abstract syntax tree generated by the parser and do a couple of things with it. The first thing it does is it expands any macros included in the code. So let's look back at our original source code, and we see we use a print line statement here. Print line is actually a macro, which means this line at this stage will be expanded to something that looks like this. This is what the full print line macro looks like when it is expanded. And this is how it would be represented in the abstract syntax tree. It also, at this point, it being the compiler, desugars certain constructs, that syntactic sugar that makes writing Rust so delightful. For example, in Rust, the for loop is a piece of syntactic sugar for an iterator. If we were to desugar this section of code, desugar this for loop, it would consist of both a match statement and a loop. The functionality of the code when it's expanded like this or when it's desugared like this is identical, but desugaring makes it easier for the compiler to understand and to optimize it. We use the sugar, the syntactic sugar, to make it easier for humans to write and understand the code. We desugar to make it easier for the compiler, for machines to understand and to optimize it. Additionally, at this time, the compiler will resolve any imports in the code. So if you're writing a piece of Rust code that brings in external crates or uses internal crates or modules, these would be resolved here as well. And we're not done yet. The Rust compiler will then take, or as we said, the Rust compiler takes that abstract syntax tree, it expands the macros, it desugars it, and that converts it into that abstract syntax tree into the higher level intermediate representation, or HIR. And let's pause here and take a closer look at the HIR. It helps in learning about the HIR to understand what the data structures are that make it up. So the first data structure is a node. This corresponds to a specific piece of code, and this is identified by an HIR ID. And that node belongs to a definition. A definition is an item in the crate we are compiling. These are primarily top-level items within the crate, and this is identified by a def ID. And a definition is owned by a crate. This is what we are compiling with Rust. It stores the contents of the crate we are compiling and additionally creates a number of maps and other things that help us organize the content for easier access throughout the compilation process. This crate is identified with a crate num. So if we look back at our original source code that we're compiling, and again, focus here on this for loop in particular, remember, At this point, this for loop has been desugared into a match statement and a loop. If we look at the node in the HIR, the higher level intermediate representation that represents this match statement, we would see something similar to this. And this is a little hard to read for humans, so let's break this down step by step. The ARM structure represents an arm of the match expression. Match expressions often, depending on some sort of condition, do one thing. If that condition is not met, they do another. So the arm represents a particular arm of the match representation. And first, we have the 8 within that arm. We have the HIR ID for this piece of code. So this identifies a node within the HIR. It corresponds to a specific piece of code. And that node is owned by a definition. The definition is some top-level item in the crate. And that definition data structure is owned by a crate data structure. So our node is a node. So our for loop is a node within a definition of our crate. That's how we can identify where this node corresponds to in the original not desugared piece of source code. And how we keep track of where in the original source code these nodes correspond to is through using what's called a span. The span stores the file path, line numbers, and column numbers of the original source code. This will be very important in the future as we optimize and desugar the Rust code. If we encounter a problem with the code after it is desugared and optimized, we really still want to be able to show the user where in their original source code that it was that generated the error. If we were to show them where in the desugared code the error was generated, which is different from the code they originally wrote, it really wouldn't mean much to them. And the whole point of tracking this is to provide meaning to the user. Next, the compiler then takes that HIR, that higher level intermediate representation that we just created, and lowers it again into the mid-level intermediate representation, also known as the MIR. And again, in order to understand the MIR, let's take a look at the data structures that make it up. The MIR is constructed as a control flow graph. The units within this graph are called basic blocks, which are identified with values like BB0 and BB1. And yes, that does mean there's a BB8 basic block in Rust code. Now within these blocks, each has a sequence of statements that execute in order. The very last statement in the block is known as a terminator. This controls when and how the program proceeds to another basic block. This is a pretty simple example. There's only one direction the basic block can go. However, if we had an if-else statement in our code, if a condition was met, we would do one thing. If that condition was not met, we would do something else. Then the terminator of BB0 would have the option to proceed to BB1 if the condition is met, or to BB2 if the condition is not met. In this case, there is more than one path that the program can take when it encounters a terminator within a basic block. At this point, I'd like to acknowledge, if you are wondering if there are more data structures that make up the MIR, there definitely are. And if you're curious about them, again, check out that guide to Rust C development. It is such a helpful resource. Let's go back to our desugared code. And let's focus on this match statement, which is assigned to a variable called result. If we looked at the MIR for this piece of code, it would look similar to this. And I have simplified this quite a bit for the sake of appearing on a slide. MIR, in the top left, we have our basic block, which is identified B2. And then we have what is called a local. A local in the MIR represents a place in memory, or more specifically, a place on the stack frame. In this case, _5 corresponds to the value of the variable result. And like in the nodes in the HIR, the piece of original, we have a span. The span is the piece of the original Rust source code that each node in the MIR corresponds to. Again, if we encounter an error when we're operating within the MIR, we can still easily track and refer to what lines in the original source code caused the error and surface that information back to the user. And that brings us to the third stage of the Rust compiler. And this one is really big in the Rust compiler specifically, semantic analysis. This is where the compiler tries to figure out what you, the programmer, are trying to do in a way the compiler can understand it and then translate it into machine code, translate it into something your computer can execute. And, whoop, looks like I went back a slide rather than forward. There we go. And at this point, after the Rust compiler has previously lowered the HIR into the MIR, the compiler will run several checks on the code, including the borrow checker. And we'll come back and dive deep into that borrow checker in just a few moments. But for now, let's finish up the stages of compilation and let's focus on these two final ones, optimization and code generation. These stages are where the code is transformed into an executable binary. In the Rust compiler, we use LLVM to do this for us. LLVM is a commonly used collection of modular and reusable compiler and toolchain technologies. The Rust compiler uses it to further optimize the code and generate the machine code required to run that code. Let's look at a visual of this. Before it gets to LLVM, the Rust compiler again takes that MIR that we created earlier and lowers it again into the LLVM intermediate representation, or the LLVM-IR. And if we look at the LLVM-IR, it's pretty unreadable to humans, but it looks something like this. Again, notice that we have that basic block. It's still organized into basic blocks like the MIR. And after we get our LLVM-IR, we then use LLVM itself to take that LLVM-IR and then run more optimizations on it through LLVM, and LLVM will produce machine code. And then it will link those machine code files together to produce the final binary. And that binary is what gets run when we call cargo run. And we see those numbers printed out. So at this point, we might be thinking, yay, we created Rust code, it compiled successfully. We now have a bit of an idea of how the compiler works to take that source code and make it into something the computer can execute. And at this point, as I promised, I want to go back and let's take a deeper look at the borrow checker. And in order to do that, let's use a different piece of code. And I'm going to give you a moment to look at this code, and I'll tell you up front, if you're thinking this will error out, you are right. We will see how and why that happens in just a moment. All right, let's go ahead and run through this code line by line. So first we declare the variable x and give it the type of string. And then we set the value of x to the string hi rusty days. I originally used this code example at the Rusty Days conference. We then say that the variable y is equal to the value in x. The value of y is equal to the value in x. And then we attempt to print both variables, y and x. if we were to try to build this piece of code using cargo build, it would indeed return an error. And this error is a result of the borrow checker. Let's now go through how the borrow checker identified this error. The borrow checker does several things, including tracking initializations and moves. How this plays out in our code is that when we start with this first line where we declare the variable x with the type of string, x is not actually initialized yet. It won't be considered initialized until it is assigned a value. And if we looked at the MIR for this piece of code, we would see that in the MIR, x is represented by the local _1, and the local _1 is assigned the type of string. We don't have a value assigned to that local yet. Now, going back to the full code example, let's look at this line of code, where we create and assign it the high rusty days string. Now that x has a value, x is considered initialized at this point. And if we look at the MIR for this, we see that we created a new place in memory, local _2, where we store the high rusty days string. So we create this area of memory when we create that string. And then we move the value stored at _2 to be the value of _1. Remember, _1 corresponds to the x variable. So we have created a string in memory and moved that string, the value of that string, to be the value of x. Now let's look at this line, where we attempt to create the variable y and assign its value to be the value of x. This is where the value of x is moved to y. If we were to look at the MIR created for this line of code, we would see that _y is assigned, or we would see that y is assigned to the local _3. Remember, a local represents a place in memory. And _3 is given the type string. Then the value at _1, remember, that represents x, is moved to be the value of _3, which represents y. This means when we get here and we try to print x after we've moved its value, x is not initialized at this line. It's no longer initialized. So we cannot print it. And this is what generates this particular error. We're attempting to use a value of a variable after that value has been moved. And the Rust compiler says you can't do that. It doesn't just say you can't do that, though. If we take a closer look at the error level, something I'd specifically like to call out is how the compiler shows where the error was generated from in the original source code through a span. So even, sorry, someone just walked in to my office and startled me. Even though we had lowered this code to MIR, or mid-level representation, we still tracked what items in the MIR corresponded to what places in the original Rust code. This is very helpful to the end user. What is also helpful is this. The Rust compiler, the great thing about it is it not only tells you what the error is and where it is, it also gives you a command to get even more information about the error so you can fix it. You are never alone when you are writing Rust code. The compiler is always there to help you. So if we run this command, we not only see an explanation of the error, we also see a piece of example code that would generate it. Then the message gives you even more information about how to fix it. This suggests using a reference to borrow a value rather than attempting to move the value, which is what we saw was being done in the MIR representation of our code. So let's follow this advice And let's change this line so that y is assigned to a reference to the value of x rather than moving the value of x to be the value of y. So if we were to run cargo run at this point, the compiler would go ahead and build the code and execute it. And we'd see the hot message, "Hi, Rusty Days," printed out twice. We've printed out the value of x and the value of y. So rather than fighting the borrow checker, we used it to make our code even better. And along with tracking initializations and moves, the borrow checker also deals with lifetime inference. Let's go over exactly what this means. Rust uses the word lifetime in two distinct ways. The first way is to refer to the lifetime of a value. That's the span of time before the value gets freed. Another word for referring to the lifetime of a value is referring to the variable scope. And let's see how this plays out in our code example. Let's go back to the uncorrected code and let's take a look at this first line where we assign the value of x to be this string. At this point, x is initialized, x is live, its lifetime begins here. When we get to here and we move the value of x to be the value of y, this is the end of Rust lifetime, or this is the end of x's lifetime. And when we get down here and we try to use x again, x's lifetime is over. It's dead. The lifetime of x is no longer in effect. That's why the program in this form will error. The other way Rust uses lifetime is to refer to the lifetime of a reference to a value. This is the span of code in which the reference can be used. So now let's look at the corrected code, where we assign the value of y to be a reference to the value of x. And if we focus on this line in particular, and we look at the MIR for this line of code, we remember that the local _1 refers to x, and the local _3 in the MIR refers to y. And we see that the _3 local is assigned a reference to the value of _1. And so this code would work. But let's look back at it and let's look at another example of lifetimes and let's alter this just a little bit to make it more interesting. Let's try to drop the value of x before we try to print out the value of y. If we do this and we run cargo build, when we try to build this code, we will get an error. The error is that we cannot drop the value of x because it is borrowed and that borrow is used later. The borrow checker tells us that x, because it is referenced by y, needs to stay alive for at least as long as y needs to stay alive. X's lifetime must be greater than or equal to y's. Looking at this in the code, again, this is x's lifetime. This is the lifetime of x. That lifetime is no longer effect when we drop x. And this is what needs to be the lifetime of y in order to be able to print it out. Remember, y is a reference to x. So notice that even though they do overlap, x's lifetime ends before y's lifetime is supposed to end. And at this point, once we drop x, y can no longer reference the value of x after this line. And at this point, when we get to the very end, x would be dead, along with y. So in order for this code to compile, the lifetime of x must be at least as long as the lifetime of y. This is key to remember when you're working with references in your code. The overarching way the scope and the lifetime of a reference relate to each other is if you make a reference to a value, the lifetime of that reference cannot outlive the scope of the value. As I wrap up, as I move toward concluding this presentation, I want to make sure you know that there is so much more to the Rust compiler and the borrow checker. Again, please, 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 if you want to know more, check out the guide to Rust C development. It is a fantastic resource. It has been enormously helpful to me personally. So going back to this question from the beginning, is the borrow checker a friend or a foe? Well, I say it's a friend, though a very strict one. But the best thing about this friend is the friend will not only tell you when you do something wrong, they will also tell you how to fix it. And I find that to be one of the best qualities I can find in a friend, as well as one of the best qualities I can find in a compiler. Thank you. And I think we still have a few minutes, so I am going to pull up the Twitch chat and see if there were any questions. Sorry, I'm having a little bit of a delay. I'm actually going to unshare my screen. You should be able to see me, but then I'll be using less memory. Haha, that is scrolling so much better now. So let's see where this started. All right, looking through all of the thank yous to Tim. That is a great thing to do. +1 for This Week in Rust. It's great. I am super glad to hear that. I'm glad to hear you like that. I'm honored by how much impact that seems to have on the Rust community. All right, looking for regarding, oh, cool. Good reference for OOP there. Why does Rust use glibc? I honestly don't know the answer to that. That might be in that Rust C compiler book, but that's something I will look up. All right, there's a Reddit. Okay. Oh, looks like some people answered that. Cool. Well, thank you, community, for answering that. I'm still looking for questions. It's dangerous to go alone. Here, take this, hands over Rust borrow checker. I love that. I love that so much. I mean, this has been such a lonely year, to be honest, and I will take that connection of that guidance from anywhere that I can find it of what I should be doing next. So I feel like I carry the experience of all Rust programmers with me anytime I'm using the compiler. Glad that the why after a move in LLDB the old value is still there. Let's see here. The value, it doesn't, while it's no longer assigned to the variable, the variable doesn't actually get dropped until it goes out of scope. So until the end of the function or until the end of the if statement, whatever it is you're using. How to get MRI and HRI? I can answer this. At least I think it's for both of them. So if you go to the Rust playground and you put in some code, in the upper left, you'll see a button that you can click on, and you can see the MRI and HRI for that code. This is how I was able to compile the examples for this talk. So definitely check out the Rust playground. Is the conference recording going to be available later on YouTube? I think so. If not, there is another. I did give this talk previously at another conference, and that video is definitely up. So I hope it can be a good resource for people as you learn compiler hacking. And I think that's about the end for the questions. So I think I'm going to go ahead and end there. I am not in the Discord presently, but I'm about to join it. So if you have further questions, feel free to ping me on the Discord. Feel free to tweet at me, and have a wonderful day, everyone.
Hello, everyone. Let me introduce myself. My name is Pierre Krieger, also known as Tomaka or Tomaka17. You can see my social media on the bottom right corner. And this talk is about running Rust inside of a web browser. But as an introduction, let's take a quick look at what is WebAssembly. Sorry, I assume that most of you already know kind of what WebAssembly is, but I'd like to give some reminders. WebAssembly is what you would call a compilation target. Step 1, you take your program, be it in Rust, C, C++, whatever language supports WebAssembly. You compile your program to WebAssembly. You deploy your WebAssembly file, your Wasm file, just as if it was a JavaScript file. And then users download your Wasm file from your web server, and their browsers execute it, and therefore execute your program. It's therefore a way to distribute your program written in whatever language you want. And this idea of being able to write your program in a language or in JavaScript is very powerful. It revisits the dream of compile once, run everywhere. Kind of what the Java programming language promised in the 1990s, but this time better in my opinion. Also what Node.js promised, the idea of having the same code running the front end and the back end, more recently than what Java promised, but this time with a different language, JavaScript. WebAssembly is widely supported nowadays. This screenshot is from the website Can I Use, and as you can see, 92% of the browsers, of the users' browsers worldwide support WebAssembly. So that's obviously depending on who you're targeting, but in my opinion, it's fine to just assume that everyone supports WebAssembly. But let's take a look at why Rust. To give some context, WebAssembly is supported by basically any language you want. You can take any language in theory, not in practice, but in theory, you can take any language, compile it to WebAssembly. So why would you choose Rust in particular? First of all, well, it just works. We have WebAssembly very well supported in the language itself. You just run 2 commands, rust up target add to install the standard library for WebAssembly, and cargo build, you pass the target, and in theory, it just works. In practice, not so well. We're going to cover this later, but in theory, it just works. Rust is also a language focused on performances, and that's what is missing from JavaScript world. If you want to execute some CPU-heavy scripts on the browser, JavaScript's not the best language for this, and so something better is to use, for instance, Rust. And the ecosystem, in the Rust ecosystem, already widely supports WebAssembly. We have excellent tooling. We have excellent crates, Wasm, bindgen, js-sys, web-sys. In terms of tooling, we have this tool Wasm pack. You just execute Wasm pack on your Rust code and generate some JavaScript binding and the Wasm that goes with it, and you can directly use it. Twiggy, which I also mentioned, measures the size of your Wasm file and says which parts of the code are the heaviest. And many crates in the general Rust ecosystem, such as the rand crate for randomness, futures timer, that kind of low-level crates already support WebAssembly very well. So that's a point for us. And before going on, I'd like to tell the success story of basically why I'm giving this talk. The company I'm working for, Parity, has this project named Polkadot and this framework named Substrate, which Polkadot uses. There are 2 of the biggest open source Rust repositories around right now, around 450,000 lines of code, not counting dependencies, just the Polkadot and Substrate code bases alone, which is kind of big, not huge, but big enough that it can be considered like a heavy code base. It was started already 3 years ago from code written 5 years ago, so it's already got lots of legacy parts. And it takes a long time to compile. That's a bit off topic, but my computer takes basically 70 minutes to compile it to give a general idea of the way for this code base. And despite this huge pile of code, well, compiling for WebAssembly just works. You type this command, it compiles. You wait a long time. So step 1, you wait a long time. Step 2, it compiles, and just works. But so this works right now, but to get to this point, we had to do a lot of changes to the code base, which I'm going to go through now, so that you can adjust your own code base to make it compile for WebAssembly. There are some traps, which I call caveats here, some traps that you have to avoid if you want to have your program run successfully. First thing to know is that it's way easier to make compile for WebAssembly if everything is pure Rust. Some Rust libraries, unfortunately, need C and C++ code. They are just wrappers around existing C and C++ libraries. And when you try to compile the Rust library, it internally compiles some C and C++ code. And unfortunately, that's a problem because not all systems have a C or C++ compiler capable of compiling for WebAssembly. If I'm not mistaken, support for WebAssembly came to Clang 8. I don't think js-sys supports it, but I might be totally wrong. I think Clang 8 supports WebAssembly, but this is still pretty recent, and you're not certain that your system supports it. Here are some example problematic crates in the general Rust ecosystem, some widely used crates. I'm not talking about some little crates that someone wrote in 10 minutes. I'm talking about huge crates. Ring, which is a cryptographic library which uses inline assembly. This does not play so well with WebAssembly. It's kind of a problem to port to WebAssembly because WebAssembly doesn't have constant time instructions. So it's a bit risky to actually port it. OpenSSL, which you might know, the cryptographic library as well, which is C code, is also problematic. Sodium oxide is also a cryptographic library. Again, problematic for the same reason. And all crates that depend on Ring, OpenSSL, sodium oxide have obviously issues compiling for WebAssembly because they use Ring, OpenSSL, sodium oxide as dependencies. This includes, for instance, the REST TLS crate, the very popular REST TLS crate, Hyper, for instance, and so on and so forth. So the three crates that I enumerated here are all three cryptographic libraries. You can basically summarize problematic crates as cryptographic crates. That's a bit of a shortcut, but it's almost true. To the point that it's usually a better idea to have a wide list of cryptographic crates that compile for WebAssembly rather than have a blacklist. Sorry. So if you want your code to work to compile for WebAssembly, better choose one of these crates. The general Dalek project, ED 2019 and Curve 2019, just compile very well. libsecp, I made a mistake on my side, sorry for that. libsecp 256k1 does compile for WebAssembly, but secp 256k1 alone does not compile for WebAssembly because it uses C code under the hood. Yeah, so use one of these libraries. One alternative, for instance, for RSA is to use the Web Crypto API instead of trying to actually do the cryptographic primitives in Rust. You just call JavaScript functions from the browser that do the same. Second trap to avoid, second caveat when compiling Rust to WebAssembly is I/O code. So what I call I/O code is any code that uses the general environment, the operating system. Why is that a problem? Because you don't have an operating system. You cannot, for instance, open a file, you cannot open a TCP connection, you cannot spawn a separate process, you cannot spawn a thread. It does make sense when I say it this way. It's obvious that in a browser you cannot open a file or a TCP connection. But if you take an existing code base, a huge existing code base, it might just say open files deep into some deeply nested module that no one touched for the past 5 years. So you might have to refactor that if you cannot just take an existing code base and expect it to compile unless you make sure that the I/O code is disabled. So as I mentioned, that's problematic if it's deep within the code. It's not problematic if it's in the upper layers of the API, because that's usually easy to disable. It's more problematic if it's deep within some modules hierarchy. A solution to that, avoid mixing the I/O code from non-I with non-I/O code. So as I mentioned, any code that accesses files, opens TCP sockets, or for instance, read command line arguments. There's no command line arguments in WebAssembly. There's no environment variables in WebAssembly. All this code must be easy to disable. And I forgot to mention, this is slightly off topic, but I would strongly encourage to do this in general, not specifically if you want to compile for WebAssembly, but just in general. It's good software design, in my opinion, to make this easy to disable. So I give a concrete example. This is what you should not do. This API you should not expose. Send HTTP request where you pass a string for the domain name and the path and the URL to send the HTTP request to. So don't have this function which you would call like send HTTP request to example.com. I also recommend avoiding platform-specific code. I show this example below where if you compile for an unknown OS, which is WebAssembly, you would use XML HTTP request from a web-sys crate. And if you're not compiling for WebAssembly, you're using the regular TCP connections from a standard array. This is a possibility, but I also recommend avoiding it because it makes everything way more complicated. The solution that I would recommend is to inject an existing socket into a function and not have a function itself create the socket. Again, what I mentioned, isolate the I/O code from a non-I/O code. The make HTTP request function here is non-I/O code, and what would call it would contain the I/O code. Next problem is time management. So this is a small part of the previous point. What I call time is basically getting the value of the current clock, the monotonic clock or the system clock, basically knowing when is the current moment, where we are in time. Calling std time instant now just panics because the standard library has no way to know how to retrieve the current time. The problem with the time, so you might say this is I/O code, the same thing I mentioned earlier. So you might think just inject the time through some API, but this is not great. This is not a great solution because time is really annoying to isolate. In practice, if you try it, having to call a function to update the time or having to inject as a kind of dependency injection pattern, having to inject a function that provides the time, all these patterns are very annoying to deal with. What I would suggest instead for the time is to have this hacky solution, this platform-specific code, and through, for instance, a crate name Wasm timer. So small disclaimer, I'm the author of Wasm timer, so use it or not. I'm just mentioning it because it's the one I know. It provides the instant and delay types, instant to know when we are and delay to sleep for a certain time. And it contains some platform-specific code that abstracts over the desktop and the browser. It uses web-sys under the hood. And instead of using std time something, you just use Wasm timer something, and it works for both the browser and the desktop. The next issue that you might have to deal with is the lack of threads. So in the browser, everything's single-threaded. This is the case for JavaScript. This is the case for WebAssembly. There exists a proposal being worked on right now to enable multi-threading for WebAssembly, but this is not going to come anytime soon. There's lots of problems to deal with, notably with atomic variables. You have to snip until an atomic variable gets a certain value. All these kind of design issues are not totally resolved yet. So multi-threading is coming, but it's not there yet. And for the moment, you just have to assume that everything is single-threaded. In order to solve this, what you should do, in my opinion, is use asynchronous Rust. So asynchronous Rust, I'm not going to go into the detail of what asynchronous Rust is, because it's a very broad topic. Basically covers the async await feature that has been shipped a year ago or so. Asynchronous Rust consists in having cooperative multitasking. Instead of having threads running in parallel, where each thread basically runs in parallel, each thread runs in parallel of the others. Here you would have small tasks that explicitly say interrupt the current task and start executing another one. So you still have many threads of executions running, but not in parallel. Just you execute a little bit of one, you explicitly yield, you interrupt the current task in order to start running a little bit of the next task, which then interrupts itself to execute a little bit of the next one, and so on and so forth. So all these light wave threads are being run in the single core, in a single CPU core, in a single operating system thread, if you want. And since it's cooperative multitasking, cooperative means that they explicitly say, interrupt me now. And it's not the operating system or the environment that interrupts the thread, but the thread itself that says, interrupt me now. So to plug asynchronous Rust into the general environment, the browser environment, you have to use like some executing context. So all the system where these lightweight threads go one next to the other doesn't exist magically. And we have this crate called Wasm by Ingent Futures, which provides a method called spawn local, which makes it possible to spawn a task in the background. So it's the same idea. The task says when it interrupts itself, but this time it's handled automatically for you. The scheduling of tasks is handled automatically for you. One consequence, however, for the lack of threads and having to use asynchronous Rust is you cannot just start a CPU-heavy processing and expect things to work. You need to break down long-running CPU tasks. So what I mean by that, don't do this example here. In this example here, I'm spawning a task in the background that iterates 50,000 times, and that does some CPU-heavy tasks. So this is kind of a pseudocode. It's not actual code. But in this example, I'm verifying a public key, which is kind of CPU-heavy. And doing it 50,000 times can take, I don't know, minutes, 30 seconds or minutes, or basically a very long time. With this constraint that everything is single-threaded, you're just going to block the entire browser and all your other tasks for minutes, which is obviously not great. Instead, after each verification, so each verification, each call to verify takes a small amount of time. And after, what I would suggest is after every single verification, you explicitly yield. You say, I want this task to stop executing to leave space for other tasks. Unfortunately, there is no way to do that. There is no crate in the ecosystem that provides a way to easily do that. If I'm not mistaken, there might be one, but I don't know it. So you can write this little snippet, this little poll fn. The first time this little function is called, it's going to return poll pending, which basically means interrupt the task, and the second time it's going to be ready. I just realized that I made a mistake here. I'm sorry for that. You will need to wake up the current context before returning poll pending. I cannot make the modification now, but basically the idea is there. You should yield the current task at each iteration. And to finish, I'd like to mention WASI. So what is WASI? WASI stands for WebAssembly System Interface. You can find it on wasi.dev. It's still a work in progress. It's not finished yet. But all these caveats that I mentioned about the lack of environment, so no access to files, no threads, no paths, no TCP sockets, and so on and so forth. This is basically solved by WASI. WebAssembly itself does not specify any environment, which is why you don't have any environment available to you. But WASI is WebAssembly plus an environment. What I mean by environment is the following: a file system, access to a clock, which also solves the time issue that I mentioned, standard input and output, the command line arguments. You can execute basically programs. You can take existing programs, compile them to WebAssembly, to WASI, and they basically behave like they already are. You don't have to make any tweak. You have access to environment variables, and in the future, probably TCP and UDP sockets. They take security very seriously. The WASI design takes security very seriously. When I say you have access to a file system, you don't actually have access to the file system of a host. You only have access to a whitelist of files on the host. Basically, when the WASI program is executed, you have to pass a list of files that are accessible, and only these specific files or directories are accessible to a program and not any other. Also, each individual feature, so file system randomness, I forgot to mention randomness in the list, but that's also something provided by WASI, standard input, output, etc., socket. Each of these features can be enabled or disabled individually. Again, for security, if you don't want your WASI program to use sockets, you can just forbid it from using sockets. I didn't mention it on the slide, but you can already try ÄroRust, already supported by well. Instead of compiling for Wasm 32-unknown, you compile for Wasm 32-WASI. So same idea, you have to install the platform first, the target first, but then it should just work. But be aware that WASI is still a work in progress. It's going to change in the future. And the conclusion, assuming that you're following the good practices that I mentioned during this talk, you should be able to take any existing Rust code base or build a new Rust code base, obviously, and compile it to WebAssembly just fine. What I mean by good practices, again, resuming what I said, prefer pure Rust crates, in particular when it comes to cryptographic crates, prefer ones that you know work already well enough for WebAssembly. Separate I/O from non-I/O code, prefer writing code that only uses the CPU and memory, and inject the operating system specific parts into them through higher level API, through higher level code, and avoid platform specific code because that's just a hack and you might regret it later. Use asynchronous Rust. You only have a single thread, so you cannot spawn threads. SD thread spawn is going to not work ever in WebAssembly. Well, it's going to work if WebAssembly gets threads, but right now it's not going to work. So you have to use asynchronous Rust. And same idea, in my opinion, it's a better software design in general to use asynchronous Rust rather than synchronous Rust. Don't rely on more than one thread. Again, same idea. You cannot just spawn a CPU-heavy task in the background and expect it to work fine. You have to be a bit smarter than that. But if you follow these good practices, you should be able to compile WebAssembly for Rust for WebAssembly now. Everything is ready. I encourage you to try it. It's amazing. You can take the same program and compiling for WebAssembly and for desktop. The same code works in both cases. As I mentioned, we have this success story of this huge code base, 450K lines of code. It just compiles both for desktop and WebAssembly just fine. And that's it. Again, social media on the bottom left, on the bottom right, if you want to follow me. And thank you.
Hey, this is Raimu. This talk is going to be about some of the things that I learned as a longtime C++ developer when I decided to learn Rust. What are the things that I recognized from C++? What things were different? What kind of stood out to me as important to learn? And then what were some of the common mistakes that I made? My perspective as learning Rust, which was only about a month and a half ago, at first looked pretty similar to what I already knew. I could read and understand the examples in the first few chapters of the Rust book, but looks can be deceiving, right? Lifetimes and borrow checking, to me, were very new, but also kind of welcome additions in a certain sense, because I thought that the strictness of the language was very appealing, that if we can catch more mistakes at compile time, we won't have to find them at runtime. How strange and strict they can be, though. Ran into a lot of compiler errors. Didn't understand how to deal with them until I got more and more used to it. So after some culture shock, I had the realization that strict can be good. The language does guide you towards better designs. Many times once the compiler gives you its blessing, it just works, right? So a few concepts in particular stood out to me as important and different from other languages, particularly C++, and I'd like to talk about them today. Also, a few types of problems that I ran into seem to occur more frequently than others. So, my initial approach to Rust was, let me form associations between what I already knew in C++ and what's in Rust. So I found these plentiful and readily available. So for example, void in C++ is the empty unit in Rust. All right, so what I learned, which was different from C++ that I tried to focus on, some important things, were to embrace the patterns involved with enumerations and with match and if-let and those kinds of constructs. So in this example, we are looking at the return value of a function called lookup. And this was a little bit strange at first, the syntax that you kind of have to read it not from left to right, but kind of from right to left, where you're calling this function lookup with an argument and you get back something that has to match a certain pattern. In this case, it has to be a sum value for an option enum. And then if it is, let's take a look at what's inside of that sum, which is that record. And the match in Rust, very similar to the C++ switch, right? Instead of cases, we have these arms, where we have more flexible and powerful matching syntax. But otherwise, pretty similar. This, though, comes up a lot in Rust, where you have to deal with the enumerations and then the structure of matches and if-lets. And it took me a bit of time to get used to that. I still feel like I don't quite know how to write it the most idiomatic way, but it's definitely a little bit different. So the second thing that I noticed in Rust, which was not so common in C++, at least the code that I've seen, is the usage of method chaining and combinators, especially when it comes to the types option, result, iterator, source, and sync. They all seem to have these families of functions you can call, which you can chain together, and can also manipulate input to output in these chains, so that you can do quite a lot in one statement just by chaining one function call to the next. So the third thing that I really needed to get used to, and this is a more recent addition to Rust, but very welcome that it's there, is the concept of futures and streams in asynchronous programming in general. So it's quite a bit different in C++. So in Rust, I had to get familiar with the concept that when you mark something as async, that it is going to return a future, and then you have the syntax where you can wait on a future if you're running in the context of an executor. And along with features, you have the concepts of sources and sinks, which are kind of like the chaining of processing, but in this case, it's with futures. And this I'm still trying to get used to, but it is a very powerful way to describe a lot of asynchronicity in your program, and not something that you would see typically in C++. So that said, let's get into some traps. So these are problems that I ran into trying to write my own code, where I kind of scratched my head, banged my head against the wall a few times, and after I ran into the same kinds of mistakes multiple times, I kind of got used to what's the common misconception that I had. So number one, unintentional moves. So this comes from, I believe, the fact that in C++, you usually don't move data. You're usually either passing references or you are passing copies, whereas in Rust, the default semantics is move. So I tended to write code like this, where I said, let me take the self.state and let me match it against this variant, see if it's an open state. And then I would run into this problem. Can't move out of self state. And I'd be like, what the heck? I'm not trying to move anything. And then I had to remember that, yes, you need to borrow that state and its contents. Otherwise, you're going to be plucking it out, and you can't do that when the state is a member of a larger object. So similarly, if we're actually going to be looking at something in order to modify it, you have to borrow it mutably so that you can change its contents. And this misconception I had learning Rust comes from the fact that in C++, there really is no difference in the caller's point of view whether you're borrowing mutably or not. You don't have to add that MUT syntax token. All right, second trap that I found myself running into a lot. This might be familiar to some of you. It is the multi-borrow problem, where you are running afoul of the borrow checker because you have the same object with many pieces and you're trying to use many pieces at the same time, particularly if you're going to be using a structure which has a function implementation and then you try to pass some of itself to that function. So we get this error message that I come to realize is a sign that I am doing a multi-borrow. So one solution, of course, is to not borrow for the duration of the function call, but borrow it just long enough to get a copy or a clone. So we're still doing the same number of allocations, but we moved it into the caller instead of the callee and kind of separated the two borrows out. All right, the third kind of trap, and this is the most hairy kind of trap that I continue to run into, is borrows escaping closures. So in C++, they call closures lambda expressions or anonymous functions, and they're a lot more loose. So you can go right ahead and hold a reference forever when you shouldn't. And the compiler doesn't care. In Rust, it cares a lot. So here's an example where we have a closure that is going to be mutating a variable, which is a string. And this is fine, right? This doesn't have any compiler errors because we are going to be using the closure and then not needing it again at the point at the last line there where we're going to be printing out the name. The moment that you introduce another use for that name, another borrow, you get into this problem where you have the variable borrowed inside the closure and outside. It gets even worse if you decide to make that closure asynchronous, because not only now are you capturing that reference to name, you are holding on to it much longer to the compiler's point of view, because this closure actually returns a future, which is itself something that doesn't complete until possibly later. So one way I've learned how to solve this and work around it is to use the ref cell or the cell types which employ interior mutability. In this case, our closure doesn't need to hold on to a mutable reference to something. It can use an immutable reference and share it, and it's a lot more flexible. And at the point where we need to mutate it, we at runtime do the borrow checking, and all's well. So, key takeaways that I hope you get from this talk is that if you're coming from the perspective of C++ developer learning Rust, try to leverage your existing knowledge. Many concepts and syntax are the same or similar, but embrace the common Rust patterns that are different than what you might have gotten used to in C++. For example, match, if, let, and patterns, very flexible and powerful tools. Method chaining and combinators, used a lot more frequently in my experience in Rust. And then the syntax that comes with asynchronous code, futures and streams, come into play more and more in modern Rust. At the same time, you need to learn how to spot traps that are particular to the differences between C++ and Rust. For example, unintentional moves, multi-borrows, and borrows escaping closures. The key thing, in my experience, is to recognize when the compiler is trying to tell you about a certain category of error and see that, oh, once again, I'm letting a borrow escape a closure. That's what that error message means. Anyway, that's from my experience learning Rust as a C++ developer. Thank you for watching.
Hey. All right, so looks like we're live. Awesome. So today, I'm going to be talking to you about Rust Wasm, and you too. So first off, this is all going to be web specific. You can do Rust Wasm stuff with Node. I'm not going to be touching that at all. This is just the front end. So Node-sys exists. This isn't part of it. About me, I'm a full stack developer at Fresh Consulting. We're a client agency in Seattle. Do a lot of stuff, front end, back end, hardware. Just it's an awesome place to work. And I've been there for like 5 years now, so stoked. I also stream on Twitch. I'm streaming to my secondary channel right now just to, be ready for things. And yeah, I have an awesome hoodie collection. I'm also a former snowboard bum, and what I have left over from that is basically just a bad shoulder. So to start things off, first we need a joke. What is a U developer's favorite song? It's not unusual. All right, so we're going to start talking about U. What is it? What does it mean? U is a type of tree. So maybe using that knowledge, you can understand that it takes inspiration from Elm. A lot of the stuff we're going to be dealing with looks a lot like maybe how Elm might deal with some of that stuff. So it's a modern Rust framework for creating multi-threaded front-end web apps with WebAssembly. Notice how I said multi-threaded here. So the earlier talk about WebAssembly was just the bare minimum. This here actually allows you to do so much more because there's a framework abstracting away some of that stuff. And we'll get into where some of that multi-threading can actually be useful. Cool. So first things first, when I look at a project I'm trying to use, something like U, a framework, I want to look at, is it healthy? So it's been going since 2017. That's pretty awesome, right? It's had, at the time I did this screenshot, from August 2nd to September 2nd, 20 closed issues, 7 open pull requests, 51 merge pull requests, 71 authors contributing. It's not just one guy. That's a good, healthy project to me. So I like it. So, other part of my title. We talked about, well, you guys know Rust. We talked about U. What is Wasm? You heard a little bit earlier, so I don't need to go into too much depth, but let's just once over it real quick. In its own words, it's a binary instruction format for a stack-based virtual machine, a portable compilation target for programming languages, meaning if your language supports compiling to WebAssembly, you can just then run it in browsers. So if you wanted to use C#, Blazor is a really cool way of just a big framework shipping like the DOM changes back and forth, and Wasm doing all the rendering and magic, and it's very cool. It's very full-featured like U is, but then some of these other things are a lot more low-level. Still really cool stuff to work with depending on what you're trying to do. Can't have a talk about WebAssembly or Wasm without pointing out the birth and death of JavaScript. This was made in 2014, maybe 2015, I forget the exact date. But yeah, he saw the future of all this stuff coming along. It was really cool. And it's just entertaining. He has a good satire to it, a good theme and premise. And yeah, you're going to be entertained all the way through. And you're going to even learn a bit as he starts talking about why it's important. But really, I'm here to just talk about U. We can just accept it's important and then move on and learn about how to use a thing. So today we're going to get started on just trying to install it maybe. So the setup, make sure you have Rust installed and Cargo. Rust up is recommended. It's like NVM or some type of version changing tooling. A lot of the stuff I'm going to be talking about today is geared towards web developers. Just because I'm a web developer, it's what I'm used to. And yeah, it's my context. However, I am going to try and make sure I'm explaining some of these web development terms for everyone else too. After you've gotten Rust up, you're going to need some tooling, Wasm Pack, Wasm Bind Gen, Cargo Web. Remember, this is the manual process. What we're going to go through next is actually way easier. For the most part, Wasm Bind Gen is used underneath in Wasm Pack, but you don't really want to bind to it only that just yourself because it's a lot of just glue. Right? We can use stuff like Wasm Pack, or Cargo Web is an older thing that I assume Wasm Pack learned from, where, yeah, they're doing a lot of the glue for us, which is nice. The best glue is a starter template, though. So you can start with something minimal using Rollup, which is just a compilation tool. It's very lightweight. Or something Webpack based. If you're used to Webpack, most of the web is currently using Webpack in their build tooling, Angular, React, etc. And then there's an unofficial parcel template. The one I used and will just be lightly demoing is this Webpack template. I made just a tiny little Game of Life clone, and you'll see a little bit of it when I talk about just what we get from using Rust and Wasm. If you're actually just looking for some like springboarded examples, U in their code has just some really good example projects such as the to-do MVC. Every project should have a to-do MVC example. How to make custom components. This is a very web-focused thing where each unit of the page is self-contained to only what you pass into it and it puts out of it. So then you get those abstractions nice and clean for composability. And then finally, there's a dashboard for doing like HTTP requests and using fetch in the browser. And there's some wrappers around that that make it just awesome and easy to use. So yeah, I just threw a bunch of words at you real quick. Let's have another joke. What is a U developer's favorite musical instrument? A ukulele. All right, so back into the framework and some of the stuff we're doing, right? The biggest feature you're going to be dealing with when doing any of this stuff is this HTML macro. It's going to behave a lot like a JSX blob in React would, or like a chunk of template within your code. So it's JSX-like. It allows us to build HTML and SVG, so dynamic SVGs controlled by Rust. Ooh, pretty cool. But you do have to be aware it is recursion limit prone, meaning your compiler is going to yell at you. It's just trying to help you out, but it will definitely yell, and you will need to increase this. In my project, we go deep with the recursion limit. I had to make it 2048, so your mileage may vary. We can take a look at some of the stuff in there real quick, and we'll go into deeper of what's happening here. But for the most part, right, we get buttons like regular HTML. We get on-click handlers for it, and we can bind to this self-callback stuff. That's basically how we propagate changes to the component we're in. We can list over things, right, iterate over them, and then take a function that returns another HTML macro and render it out here, and then collect it. So very composable, very powerful, and we can then just abstract away the things we care about to other places. And yeah, it's very clean. One thing to remember, though, this is very React-like, and because they're using a virtual DOM under the hood, they need to do this whole spaceship operator, or I forget what you call it, but it's a fragment. This is just something that gets put into the virtual DOM as a node to reference all these children. You can't just have multiple children at that top level. So if you have a bunch of these things you want to have that are not nested, they're going to be siblings, you have to nest them within one of these guys. You saw me doing a little loop there earlier. So for the most part, the render item function ends up being the common part between them. We're mapping over it. So we're just basically turning this thing into an iterator. Here we just use for syntax instead of the iter then collect. Whichever one you want to do, I don't know if there's any performance differences, but I haven't noticed any myself. If you're going to do HTML, you got to be able to style it, right? So styling this, yeah, classes, HTML, that's the way to do it. You don't want to do inline styles, though there is tooling working on that. Because it's Rust, we need strong types, so the typing for that might not be complete yet. We'll get into some more of the CSS library stuff later. But this is just for adding classes to your elements, and this is how you can do a lot of the dynamic styling stuff, right? So here, hard-coded, just string, multiple, like standard HTML as well. And then we get into, yeah, because this is inside of a function context, this is just a macro, and then this is code running within your render, this entire thing can have functions run. So this function macro can execute inside of here, and we can interpolate strings. We can also use tuples to add these things together in nice, clean ways. So yeah, we can do tuples, vectors, which is a Rust term for an array. And then finally, we can just do a function that returns any one of these things above. So it's very powerful, very composable, and you have a lot of freedom to just do whatever you want. Next up, HTML literals, right? You got to have text, you got to have numbers in these things. You might want to do variables, etc. too. How do you do that? Well, variables inside of a node will definitely need to be wrapped in these brackets. This is familiar to some React developers out there, for sure. Here, though, if you want to do like a raw string, you actually have to wrap it in quotes and the brackets, which is a little weird. But just understand Rust is a little stricter for reasons that are helping you out. And then finally, we can pass just raw numbers too. Still have to wrap them in brackets. Otherwise, it's going to try and interpret it as like a construct that the HTML macro should recognize, and it won't. So next up, oh, what about expressions? Yeah, you can totally do if-else as long as you are returning stuff the same way. So if we did an if here, that would make this just ambiguous about whether it returns something or it's null or whatever, right? There is no null in Rust, so that's a problem. So instead, yeah, you have to return just something, an empty HTML node if you don't want to render this thing. Something to be aware of. And keep in mind that you can also just abstract all of this into a function and clean up this context. So anytime you're going to be doing some of this like if-else type logic, it's going to clean up your HTML macro to probably do it in a self-contained place. So yeah, we talked about components, right? I've talked about a lot of it. And how do we make one? They are the fundamental building block of the modern web these days. So first, we have to consider the life cycle. How does this work? This is my own custom bit, so the creators may be able to call me out on some of these things that slightly go wrong, but in my logging, this is what it seems like it did as well, kind of lining up with what they had in their docs. So you get your created hook, as far as like when you can do code actions for your component, right? Created is when it gets, okay, here, this template needs to render this thing. And then the view gets created just one first time. After that first time, we get our rendered hook, and that allows us to access the DOM and maybe get like dynamic height values. If you have a paragraph of dynamic text going into a component, you don't know how tall it rendered, if it can grow. So you may need to take that into account and do some magic later with JavaScript or Rust. So then here, the view, this is basically the rendered callback that I mentioned earlier. The terminology changes. It's basically the same thing though. So the view gets rendered, and in this view, we are simply outputting our HTML. And we're simply going to come back into this every time we change our props, coming here from a change event, or our state from an update event. So any of these two things, these hooks will fire that we can then listen to some logic. And if we return a value from one of these as true or false, it will say whether we come back up here and re-render our view. So you can actually get some good performance optimizations by deciding not to do this backup. And then finally, when we're going to be removing this component, we got a destroyed lifecycle. That's where you clean up timers and just anything that might leak RAM. Okay, so I'm hammering through this. Were there any major questions first, real quick, guys? I just want to call it out, give you some time. Raimu set his to 9001 for the recursion limit. Nice, nice. Obvious reasons, of course. But yeah, go ahead and ask some questions here. I will be doing questions at the end, a lot more focused. I got the chat right there visible. But in the meantime, I just want to make sure I get a lot of this stuff out, and I can drill back through into the slides as we get to questions. So anyway, I mentioned props a second ago, and I'm probably talking fast, so let me breathe. When I mention props, what that means is our component takes in attributes like every HTML element does. So a title or a link, an href would be your link tag, things like that. To pass those in, we have to actually strongly type that, right? Rust needs to know everything about everything at all times. So here, we take this container props. This is going to be the thing that we're just throwing props into. It's our basic struct component. And later we have our implementation of stuff for it. But the first part is the props. We derive the properties. They have to have clone because they are clonable due to just borrow checking concerns. And then we just define what they're going to be. So children here is for rendering out stuff inside of our element. Oh, yeah, I'll get to that later, Sponge. Sorry. We'll get to some more like higher level questions at the end. But right now we're getting into like, do you have questions about what we're talking about here specifically? Next up, let's look at, how do we define like so children here are what if we have our one component, but we want to pass some generic stuff into it. And we don't care because our component doesn't have to care. It only cares about what it's rendering. So we can have a generic component that is reusable for things that we pass into it as children because HTML elements have an opening and closing. So based on that children, we can just make sure we simply render out here by doing self-zero child render. Some of this other stuff though, like what if we want to pass a string? We pass a string into our component. We can make it just props or default. And this could be, I I believe this would be just, it allows us to let it be optional instead of required. And here we can set an optional value and default it to true. So next, events. These are the things that come out of our components. So if we're inside of a button, our own custom special button that has magic happening behind the scenes, inside of that button, we maybe want to bubble up when it was clicked to the thing that created it, because we don't want to have logic in all of our places. This is very fundamental, like React type pattern, Flux. You want to bubble your changes back up and let them filter back down. In this case, we're just doing a parent-child relationship of our components, but you could also do it with something like a Redux state. So for an event, once again, we take in some props. We take in link as a prop, and then in those props, we don't actually have much happening, right? And technically, these are events for inside. These are not events passed as props. These are just events within. Sorry, forgot my context. So these events might be, we're inside of a bigger container, and this is the parent in that context. And we're maybe handling a click or handling some input into a text field, and then handling a reset to empty those out, right? To do all of these events, we're going to define that at our parent level inside of this update function. So in that enum, we list them out here, and we can have arguments, which is pretty cool. With those arguments, we can pass them along and then handle them inside of update here. And this is even going to check to make sure we're hitting every arm of that enum. So if we forget to handle one of these, it's a compiler error, and we know way ahead of time. You can actually set a fallback to just have the underscore there, but we're not doing that in this case. So here we would actually have a compiler error because I forgot to implement reset. Whoops. This is demo code, so this is not what's actually in my working project. And yeah, here we see we're returning true. So for all of these, we wanted it to re-render. We wanted it to change something. If we wanted to maybe not do that, we could short circuit this thing and return false from one of these arms. And then it would not re-render, and we'd get a performance boost to, due to not just compiling that thing or rendering the thing, sorry. Next up for a component, right? How do we actually reference the component itself? I mentioned looking at the height and trying to determine what's going on, right? Maybe you want to get a reference to some element that's inside of your context. The ref is the fundamental building block for that. And it's familiar to React developers, Angular developers, Vue developers. It's just a common abstraction now to the idea of different rendering contexts, virtual DOM, server-side, etc. So the DOM might not be there. We create a reference to it, and then we can operate on that without having to do crazy checks within our code. So basically, yeah, we create the ref. It's a prop on our component. This is all maybe like separated by a bunch of other code. And then in our HTML, we're defining that ref and cloning that value into it. So then bam, our ref is now bound. Later, when we handle a click, we can just simply check, does this thing have attributes? And we can just check that. Currently, nope. There you go. Yeah, Rocket for RESTful APIs. There's also Actix, which I've heard is very nice as well. I haven't used either. We're strictly talking about front end right now. So yeah. So here we go. We're getting into some fun stuff now. Agents. For an Angular developer, this is going to be intimately familiar. It's going to be, oh, this is just a service. Don't get confused. We have services later. So a little bit of name jumble there. But here an agent is what would accomplish maybe like your top level state, such as Redux might imply, or things like that. It's just something that exists at a dependency injected level, and we get to decide that based on how we use it and how we define it. We're going to get into some of those definitions, and this is where some of that multi-threading comes in. So yeah, agents are similar to Angular services. They're using web workers for concurrency. So this is a U abstraction. This is some of the magic we get from the framework, not just them wrapping some of the other stuff that Wasm provides, or that Rust Wasm provides. So yeah, it uses web workers under the hood for concurrency. And what is that useful for? We said shared state. We also said maybe offloading heavy computation. And it's also just for passing messages from component to component, maybe like pub sub type ways. that can get hairy really quick. The shared state via like a top level is typically easier to deal with in larger applications. When we look at their life cycle, we realize that it's almost the same as what we had with that component, right? It makes sense because, I mean, created, destroyed, obviously. But then, hold on, we get into different stuff here with connected and disconnected. So for the most part, we'll get into how that can fire with different use cases. But connected fires when we have a component listen to this thing, and then handle input and update happen. They coerce maybe the changes being bubbled down to the thing that's connected to it. And then later, disconnected is when our component maybe gets destroyed, cleans up that memory in their destroy, and then this, when it has no more connections, can destroy itself, depending on the agent we use. So now we're getting into some of those agents, right? The types are context, job, public, private. There's really two things that separate these, right? So think of it as just one of those quadrant boxes. There is things that are in our UI thread, working along with all of our other Rust code. And there are things that are in a new thread. There are things that are a singleton, and then there are things that are unique to maybe the level they were provided. So what that gives us is the singleton aspect is as if in our Angular code, we required or imported this, this service at the top level of our application, right there in the app, right? Whereas the job might be some type of individual component scrollable listener that you have bound to just a single component, and you just want to, like, you know, do some magic inside of that component as someone scrolls and you're listening to that single component. When it gets unmounted, you clean that up. So it's very much, you have a lot of power to decide what you're going to use when you want to use it. And really, yeah, the UI thread versus new thread, that's where we can get into some of those like performance intensive things. Yeah, that's why you'd want to make a new thread. You got to remember, when you make a new thread, it doesn't just have, or it does have a cost, because we have to serialize everything between threads. We don't have memory sharing between these currently in the web. So remember, there's a cost. If serializing your thing takes more CPU than just operating on it, just operate it on it in your UI thread. But recognize that putting stuff out into your new thread can improve performance for your UI thread, which will improve just overall user jank or performance perception. To communicate with one of these agents, we're going to use a bridge or dispatcher. So a bridge allows bi-directional communication. Remember that whole like pub sub type thing I was talking about? We can do it between an agent and an agent. We can do it between a component and an agent. It can act as maybe the bridge between a component and a component by being that agent in the middle. Or we can use things like a dispatcher for, let's think of like maybe our Redux level state, where we click a button, it bubbles a change out to some global thing. That agent calculates that state and spits it down back to the rest of our application. That right there, the button doesn't need to know anything about it. It doesn't even need to necessarily be that connected to the agent. It does have the connection cycle still, but it's just a lighter weight way of dealing and communicating with this thing. So memory is a concern in Rust at all times. You know, if you can only use a dispatcher or if you only need a dispatcher, boom, there you go. And yeah, we got another joke coming, so don't worry, don't worry. We're going to talk about services now, and this is where it gets confusing. Services for an Angular user are a very different thing. Here, it is just used to abstract away browser APIs. Let me take a sip. Sorry. And it's just an energy drink. No big deal. So, when we look at some of the services, it'll make more sense. It's basically the browser APIs we talk about might be local storage. You know, so here we can just read and write to it. Very simple API. Documentation is just awesome. Actually, I believe some of the documentation for these is lacking, but the examples provide the rest. And it is really just 2 lines. For using fetch, there's a little bit more to do. But once again, it's pretty easy. We get our fetch service. We have the concept of returning a fetch task. This is some of that async that we heard about earlier today in Walter's talk and the other Wasm talk. And yeah, just using asynchronous programming, we can still operate on our UI thread without pausing the world, right? To wait for this code to come back. So here, we can then get it, return the fetch, and then later async await on it and just be fine. So it's quite nice. Yeah, just return fetch service. We build our request, expect our callback to handle this response, and then done. And I did those in the wrong order, but you know what I mean. Last up, we might have something that you'll see me using later, request animation frame. This is something in the browser that allows you to just render when the CPU or the browser says it's ready for it. So you're not spamming the CPU with calculations they couldn't possibly render anyway. This is amazingly useful for games and things like that. How would you benchmark those points to know whether to serialize or not? Well, because it's Rust code, we have the option of just Rust bench. I forget the macro specifically, but we could just benchmark the individual chunks and find out, right? You could benchmark your serialization because you have to serialize it into something. That's a function you write. And you have to benchmark maybe the code you're running. So if you can unit test those properly, you can then get proper benchmarks for it and then make that decision. Does that help? Just want to make sure. Cool. So, yep, we went into, yes, request animation frame. Once again, we're just binding a callback. Here, we're doing that self-link callback because this is bound to our component lifecycle, right? And then here, yeah, we're getting into like intervals and stuff. And it's just very simple, easy to use stuff. But I do want to point out that anything you're expecting to be there for like browser APIs is most likely there. So that's cool. And when we think about what this is doing, why do we need these services? Aren't these provided by the underlying things like Rust, Wasm, or sorry, Wasm Pack or Cargo Web? They are, but because U supports both, it abstracts away and makes it so you don't have to throw checks all over your application if you wanted to maybe mix and match them or upgrade an older application. So it's pretty cool. And then finally, there's a lot more. There's, you know, keyboard stuff, resize, WebSocket, dialog, console. I didn't see one for scroll events though, but I think I just missed it. So that was my fault. Keep that in mind. And then finally, best part. Where do devs go to learn about you? Technically their documentation, but eventually maybe a university. Yeah, I know. So, man, whew. All right, let's check out some demo time. And we'll really get into like some of the performance wins we're getting from from Rust. It'll actually make it very obvious. So first, let's do this part. This is my local code running in dev mode. I know, I'm sorry, guys. The puns are just too much. But it's a good break in between. So, next up, let's just kick this thing off. In my game of life, I identify whether we are in a loop, right? An endless cycle. The way you can do that is if you get the same frame in your loop, right? You can look at every frame. If you get a duplicate frame, you know, based on the rule of life or the game of life, the rules for it, it is bam, in a loop because it is all just deterministic. So here we see a glider and we're rendering real slow. Let's go faster. So this is my Conway's game of life. We interpolate frames and leave a trail and make it try and look more like cells and stuff like that. But the part we're noticing is it starts getting really slow down there at the bottom. And as I explain it, it'll make more sense. So I just said how we have to look and like compare every frame. Well, what does that mean? That means at its most naive level, comparing every pixel of every frame until we find a duplicate. We haven't hit a duplicate yet, right? We haven't looped back over to that middle track. So instead, yeah, every frame, as we get a new one, is getting iterated pixel by pixel against the current one. And it bails out when we find a difference. So at the top, it's a difference very quickly. So bam, we can real quick at the top there, and then down here at the bottom, it's down to a crawl. Like, wow, that's really bad. It's 60 frames a second, but is it? It's dev mode, so it might not be. We'd have to profile. But hold on. Like I said, we are doing this naively. It's of the mindset, don't prematurely optimize this. We could totally make a hash of each frame and compare the hash and then do like a collision check to check each pixel of each frame. And the memory we're consuming for this is minimal. We haven't gone above 12 megs of RAM. Yeah, I'm fine with it because we're able to use proper Booleans, integers, etc. under the hood. So that makes RAM just way lighter. But if we go to the production rendered code, we'll see why I haven't done that yet. I haven't needed to. I actually optimized that whole like waviness effect before we optimize that checking because we go and do this. Now right there, we're at 2 frames a second. Let's crank it back up to the 60. And we just see it flying by. I don't even see it slowing down. Not yet. Well, that's cool. Okay. It's bound to slow down, right? Nope. So it frees us up to not worry about the performance optimization aspect, and we can just develop features first, and then go back and do it right when we notice there's an issue. So it's very cool. And yeah, rest in peace, John Conway. It's a very cool thing. He was not necessarily a huge fan of Game of Life because he believed he had better contributions, but it was still just a good way of getting people involved in it. So I think, yeah, we owe him a debt of gratitude because something like this can help inspire people to look into this stuff more. So that's what we saw. We didn't see a single slowdown there. After 800 frames, bam, every single one of them checked. I think it was something like that. Easy, no big deal, not a single performance issue. We're hitting on this machine because I'm 4K, my monitor can only paint 30 frames a second. That's what we're actually getting. So yeah, that's pretty fun, huh? So let's get back to the presentation. I think that was a good little demo there, showing off like some of the power of this thing, right? Conway's Game of Life doing all that checks. If we had done that in JavaScript, I would have had to do the major performance optimization a lot longer ago, right? Like the hashing and all that stuff. So pretty cool. As we get into this, let's start chatting about it, you know? Let's see what's inside of this. I mentioned web-sys. I mentioned standard web, right? What do those mean? Well, web-sys is Wasm bindgen and, Wasm pack type stuff. Standard web is cargo web. These are just wrappers and things together that are kind of like mixed and awesome, right? And, just know that when I say web-sys, I possibly mean Wasm bindgen. When I say standard web, I possibly mean cargo web. They're basically interchangeable in my mind, at least. When you're actually doing some of this development, you're definitely going to need to be doing some debugging, right? The tooling I used, that starter, came with a bunch of stuff already. Here's one reason, though, that you're not going to want to use cargo web these days, because console error panic here really just gives you amazing stack traces in your dev tools, right there in the browser, like bound up, giving you line numbers in your Rust code for the Wasm that's failing, which is magical, right? So very cool. So these nicer stack traces, you're going to want that. And that's why I would avoid cargo web these days. It's the older thing that maybe they were able to learn from. There's always console log. That's my favorite way of debugging. The log crate just works. You can just call out to it. And I believe it's probably just using console service type stuff under the hood. This is the U wrapper, though, so that you can get cargo web compatibility or standard web, right? So if you're already in standard web, you can just do log and move on with your day. Here we see a bunch of like the really internal stuff, like some utilities for just doing shallow prop checking and like really optimizing your code. Let me point out, I haven't had to use any of them yet, right? So without premature optimization, I still haven't had a need to actually like get into this stuff yet. I plan on it, but not yet. So yeah, NEQ assign is just not equal assign. It's one of the major performance things that they're using, possibly in like pure component here. They're memoizing based on props for the most part. When they say memoizing, it means you can cache the result of the function if you know it's always going to be the same, given the same inputs. So if you have a pure component, you can cache that result. And the HTML stuff is the biggest performance bottleneck you're going to have. So if you can eliminate HTML runs within a tree, you're good to go. Some of these other things like LRC, linked list reference linked list, reference counted smart pointer, mutable, immutable reference counted smart pointers. A lot of this is for like sharing stuff and being more memory performant. I haven't had to need that yet, though. I'm still consuming less RAM than my JavaScript code would, right, without doing major optimizations. So that's pretty cool. And finally, there's this history thing, which I wanted to make sure I got to. So that's why I kind of went through those others. History here is just a wrapper around the browser's history API. And it's this vec-deq or DQ or something like that. But it's basically like a memory performant wrapper for this thing, so you can share it around because they have to operate on this using just the router and all sorts of stuff anyway, right? And when I say router, that's a web concern that simply says, let me take this URL and turn it into a web page, right? What components do I render based on the URL? Ooh, sorry about the language there, guys. I forgot that I'm using my joke stream text. But yeah, for the most part, some really cool stuff. When you want to optimize this, you know, optimizing at runtime, it's just, you know, there's NEQ assign, there is RC for reference counting, there's non-native pure components, and there is like a missing thing for functional components. When we say functional components, this is directly relatable to like the React context of functional components using hooks, right? So that context is not here in U. We're going to go over some other stuff that is actually embracing that quicker. But when I say non-native for pure components, this is just some third-party library that is maybe implementing some of these things. So it's something to just consume and use. And then, you know, when we say optimizing, there's also another optimizing context. So there's optimizing the build size. When we say optimizing the build size, in the web, we have to worry about how much data is the user having to download to do this thing. In the case of some others that we don't need to name, they have a large payload still. They're shipping like upwards of a megabyte. In my code, I'm shipping upwards of like 300K. And, you know, there's a lot going on with my cellular life, game of life implementation. So it's a little larger. But really, all this stuff I'm getting for free using the starter template that I have. If you want to build it yourself without using a starter, yes, you're going to have to start using stuff like wealloc, a release compile profile, and Wasm opt is going to then, take your WebAssembly and run it through Binarian, which is basically like an intermediate compiler, I believe. And it's just, it's going to make it just a lot smaller. It's going to be able to optimize the size of this payload, which is cool. Now, here's where it gets a little trickier. So, sorry for it again. What word is that? That is enabled. But it is WebAssembly enabled. So wealloc is just the elfin allocator. It is just a small allocator for Rust, right? It is just something you can then put into place. It doesn't have a lot of the same panic type compilation stuff because it's in a different context. It's in the web now, so a panic is a much different thing. So there's just a lot of like listening stuff that you don't have to do anymore because you're in a different context. And you just don't need to listen to that stuff as much because the compiler hopefully got you. But here, this is maybe as developers, what we're going to care about most of our time. When we make a change in our code, how long does it take to recompile? And this here, it's important to remember, right? I said compilation time is one of the biggest things. I said the HTML macros are one of the biggest things for compilation time. It's one of the biggest things for runtime. It's just a lot of work. Oh, thank you, Docker. But the thing to remember is that, if you have a lot of stuff that produces HTML, when you change anything that is in that tree, you have to re-render basically all of it. So a better way to do it is to have a main crate in which you're going to call out to your page crates. And then you move commonly shared stuff like buttons and other widgets type stuff into like another crate. So then the best case scenario is rebuilding only the main crate and then one of your page crates. That's if you edit a page. If you end up editing the common crate, every crate that depends on it has to build anyway. So that's the worst case scenario. The problem is you actually hit that a lot when you're creating new stuff. So you can create a whole new crate. It's just like a sandbox. And that might be the way to like iterate on new components as your shared crate gets bigger. So, time for another joke. What does Batman use to climb a tree? His utility belt. Okay, so some final notes. These are some of the things just, you know, I couldn't really figure out where to put, but I thought these thoughts needed to go somewhere. We're okay on time still, I believe. So, yep, we'll keep covering these. But basically, the docs need some work, right? And keep in mind that documentation, it's all of our responsibility. I think if I do some more testing, I can totally help add to these docs, right? I maybe even have some images they can use for the life cycles if they're accurate. Stuff like that. Pardon me. So yeah, documentation is all our responsibility, and we can all help. We can even start internationalizing the docs too. Some of the things that we would expect to be there for like a real web app are also not there, right? Like styled components in like a React-y kind of way. Just binding to style parts of these components, you know, at like the attribute level. UCSS is that inline declaration kind of stuff. It would be the building block for most of these probably, right? Because it would have to be injected in at compile time. So it wouldn't be able to be that dynamic. But if other stuff can abstract these away nice and clean, then we get some real power. So some of these other things, right? I believe one of these, maybe CSS modules or CSS in Rust, is using UCSS, but I could be wrong. But here, CSS in Rust is actually aiming for like a SAS type styled components architecture. When I looked at it, I don't think it was there yet, but there's always room for improvement, and yeah, got to start somewhere. So seems awesome that there is this stuff going on. And then finally, CSS modules is if you want to import your styles directly in at the component level as if it was like an asset. This is a very like Webpack type focused idea where you could just import the CSS module and throw it onto the style tag. I believe that after the explanation that I just made, this one is the one that's using UCSS under the hood. But yeah, very powerful stuff. So what does that mean? Well, if we can get proper styled components, we can get better runtime like animation and prop changing and stuff like that. As it is now, you end up just changing classes, and that can get heavy if you don't have like, it can get heavy because not everything is static. You don't have set values you can give stuff. There's going to be dynamically sized elements that you're going to have to calculate and deal with and lay things out. So yeah, this is definitely important, and I'm looking forward to more progress. Testing, right? We showed the lack of testing there. Really, though, for just unit testing, it ends up being very similar. All we do is just Wasm bind gen test, like our regular Rust tests. We all write tests, right? Wink, wink, nudge, nudge. But yeah, here we just simply do the same thing, and this is going to run in the browser context, in like a JavaScript context, to make sure that, yeah, our tests are passing as we expect them to, which is cool. So, external libraries. This is something that the docs site says is needed, right? Think Bootstrap, Material UI, arbitrary CSS framework component wrappers, right? I used Utify, and that's where I got maybe like the drop downs here, that button. It's working pretty good. This slider, yeah, I don't mind it. So there's a lot of primitives there in some of these things, but there's still a lot that they're wrapping. Utify is just a wrapper for views, Viewtify type logic, just written in Rust and, you know, this stuff. So now, wrapping up. Thank you guys for bearing with me. You just heard me just throw a bunch of words at you. You're going to really hate me for this next one there, Saitama. So just hold your horses. Some notable other web frameworks to look at. right? There is seed. Seed is most likely the important one. They're the ones that are working on the functional components, right? React hooks type stuff. They are also just closer to what Elm might look like as far as like how the HTML macro gets put together. You're not using angle brackets in HTML anymore. You're using comma separated list of like tuples and stuff like that. Or maybe, I forget the exact syntax. But basically, yeah, you're just composing these things of functions instead of composing these things of HTML that turns into functions. Could be something you like. It's not necessarily my cup of tea, but it's another great framework where, yeah, they have good progress going, and you might want to check it out. Some of these others, I'm not familiar with at all, and when I went and looked at their repo, it didn't look as nearly up to date, so it was just disregard, because I like people continuing to work on the open source and having a good community around it. So that was just my criteria. But it maybe has stuff that solves what you need better than you, so you might want to check it out. I do want to point out, and I did ask permission for this, so thank you. There are other awesome Rust streamers you guys should check out. Raimu, you just saw earlier, that was Walter. There's Mr. Halsey, Madhouse Steve. These guys are all on Twitch by these names. And I will upload these slides with links so that it's easier for you. Togglebit is doing some Godot, which is a game framework development. Ecton is also doing his own game engine dev. We see Brooke Zerker, who's doing some really cool game dev. Ferris Streams. I was just told about this one that I don't know how to pronounce, but they're doing a Dwarf Fortress clone, which sounds fun. And then some of the other streamers that just do other stuff, like just all over the place for Rust, is Code Show. He actually runs the Rustaceans team here on Twitch currently. There's Provod, Musean, I hope I pronounced that right, Gamozo, Soding, Jonhu, Steve Klabnik, the Steve Klabnik, and Eric.dev. And these guys are just awesome. Eric.dev tends to be more back-end focused if you're looking for that. But just, I recommend every single one of these streams, guys. They're so good. So, that said, here's some citations. Most of my stuff just came from their docs, their example code, and like the Wasm Bindgen documentation. So, fantastic docs for just a web dev like me to understand this stuff. So now, and once again, Saitama, I'm saying sorry early. Is this goodbye to React, Angular, etc. for me? I don't think so. I think there's enough stuff made and enough libraries existing to where for me to be productive making a web app, I still need some of the stuff that these will just have available. That said, it could change soon. However, I can definitely name or think of one person who is definitely never going to give you up. Thank you, guys. All right, so we can get into some questions now. Yeah, you're welcome. And yeah, so I'm just watching there in the Twitch chat. Let me know if you got any. And also, if we're going over on time, you guys can let me know, and we can just cap it. Thank you. Thank you, guys. I should have done thank you right there. Oh, no. Ruined. But okay. But yeah, any other questions? Where can you find the slides? I have them available on my GitHub, which I'll be posting to Twitch chat here momentarily. I just need to get them onto the other machine. But the Manning Live, thank you guys again for this presentation opportunity. They also are collecting the slides, and I've uploaded them to there too. So should be plenty available. And yeah, I'll be providing those in chat here real quick. Very useful. All right, cool. But yeah, that does look like it. I appreciate you guys, and thank you. I am available on my Twitch stream pretty much every day, so if you have questions tomorrow or the day after or two, let me know.
Hello everyone and welcome. Probably some of you already heard that the new Mars rover of 2020 called Perseverance is on its way to the red planet, Mars. So I thought this is the perfect time to introduce you to the ÄroRust working group. Before we continue with what is ÄroRust about, first let me tell you a bit about myself and why I'm standing in front of you talking about ÄroRust. My name is Lechev, and at day I work for ADEX, which is a startup company working in the blockchain domain and advertising. And I love to travel, go to parties and go to festivals. However, due to the current situation, the current outbreak, this is not really feasible right now. It really hurts me. Thankfully, I do have other things I like, including wandering around the city like a tourist, or a nice hot or cold beer and coffee, among other things. And at night, or really in my spare time, I play around the ÄroRust working group, and I am one of the co-founders there. So, what is ÄroRust about? Really, it's all about two things. It's about Rust, and it's about aerospace. And aerospace includes everything from drones, rockets, satellites, ground stations, and so on. And as a working group, we have this goal to help and push the open source community into this new, growing, exciting industry of aerospace by providing information, materials, tools, crates, and so on to the industry itself, but also to us, the hobbyists. Lately, I also think that we are a community as well, and on that I want to extend a bit. Our community is welcoming everybody, no matter their knowledge, their experience, their expertise. Everybody is really welcome, and we enjoy sharing our passion, our love towards flying, space, and just building awesome stuff. Our community includes a variety of people, a diverse group of people, including students that are studying something related to aerospace, to people that are working or have worked in aerospace, to people like me that are just exciting to build a nice tool project or a nice hobby project. And as a working group, and of course we do work on a couple of projects, currently active ones, and I want to talk about three of them. The first one is called Splice. Splice is in this astronautical critical domain, if you wish to call it that way, as you can see on the matrix here. And Splice is a domain-specific language for software-defined satellites applications. And currently there is an OPSAT version of the minimum language specification. OPSAT is this, it's a flying laboratory, as the European Space Agency calls it, and it's a project of theirs that they provide a new hardware, new tools that people can try to build the next tools for exploration in space, as well as build awesome projects on top of them. And of course, you can find out more in the provided link on their official website. The next project or crate that I want to talk about is the NMEA 0183, and this stands for National Marine Electronics Association. I'm not really sure where to put this crate on the matrix. However, I do know what it is. The NMEA 0183, it's a data and electrical, both data and electrical specification for communication between marine electronics. And this crate is a sentence parser written in Rust. It's really nice to see multiple people from different crates, different maintainers coming together to ÄroRust to collaborate on this project and build a more feature-rich, more tested, and in general a better crate for this type of specification. Lately they did land no STD support as well, which is really exciting to see this progress. And of course, you can read more about the specification in Wikipedia. And the third project that I want to talk about is the ÄroRust. This is the project I've been working on, and it's in this aeronautical non-critical domain. And it really is about drones, in particular the Parrot drones. It's a nice platform, open platform that we can build upon. And the Parrot company makes a couple of different drones, including some that fly and some that don't fly, or even jump. And we are focusing our efforts on the flying ones. We do look to collaborate with other working groups that I'm going to mention in a bit. And of course, we did make it fly. However, there's plenty of stuff to implement, plenty of stuff to think about, including a demo project that we want to do, something practical that we can use the drone for, and this crate for. And really exciting to see what can we build with that. Of course, we have a couple of companies that have joined as well. The first one is Exodus Orbitos, and their CEO is working on the Splice project, actually. They also agreed to provide us with a platform in space to deploy Rust demo code in the future, which is really nice. And they also launched their first project, which is a CubeSat development kit, and you can check more on their website. The second company, we have a representative from them. It's KuboS, and they have a flight software framework as well as a mission control software, and they use Rust extensively as well, which is also nice. And it's great to see that there are even companies that are excited and eager to join this working group and see what can we build in it. I mentioned that we are looking to collaborate with other working groups, in particular the Rust computer vision one and the Rust machine learning one. And I don't follow the machine learning one that much. However, I do follow the computer vision one because we can do some post-processing of the video in the future for the drone demo, or even one day in real time, who knows. I want to continue with the fact that I hope this grows, and I hope more people join and bring more knowledge to the working group and are excited to really grow some project and have fun doing that. Thank you so much for listening. I am providing the links to the GitHub organization of ÄroRust, as well as a link to join Discord, where I hope to see you and greet you, as I usually do with newer people. And I'm providing the crates that I mentioned, as well as the GitHub organizations to the Rust machine learning working group, as well as the computer vision one. I hope everybody's fine and is having a good time, even in these strange, weird times. Hope you're taking care of yourself, and yeah, hopefully one day we can meet in person. Until then, welcome to Discord if you want to chat about space and yeah, build some cool stuff inside while having fun. So thank you so much. Bye-bye. Have a nice one.
Hello there. Welcome to Using Rust for Multi-Architecture Apps. My name is Michael Hausenblas, and I'm a product developer advocate in the AWS Container Service team. Before AWS, I used to work at Red Hat, Mesosphere, MapR, and in applied research. I really like to connect with you, so hit me up on Slack, Twitter, same as for Twitch, I'm Hausenblas there. I have a live stream via mh9.live, and if you prefer good old mail, here's my email address. All right. So before we get into that, I have a little hypothesis, and that is that every environment, you can call it an operating system, for example, has its native programming language. If you consider Unix, for example, that was written in C. If you look at Docker or Kubernetes, it's written in Go. So my question to you is, what is Rust's environment? Is it a browser? Is it Edge IoT? Wasm, is it the future runtime of the cloud? And there are certain indications for all of that. I just want to highlight that you typically have a dominating language. A certain environment might be written in, and with that comes a lot of system level stuff that you might want to consider. Okay, let's move on. Some examples of Rust at Amazon, at AWS, projects that we have released in the open source, we are developing as open source in the community. For example, Firecracker, which is a micro VM manager for serverless compute. You would find that in Lambda, for example, or in Fargate. You got Bottle Rocket OS, containers operating system. You got Risotto, you got Flogger, Escalono, a couple of other projects. So in a nutshell, we are doing quite some things in Rust already, and obviously we can do more. And again, if you're interested in that, please hit me up later on. So what does multi-architecture really mean? If you look at good old Wikipedia and you look at instruction set architecture, ISA, there's quite a lot of, a lot of candidates out there. And although we probably widely daily use, only have a handful of architectures, 86, 64-bit, ARM 64-bit comes to mind. You can see that there are quite a lot of ISA, a lot of instruction set architectures available. So this is, or can be, a challenge. If you think about how your application, that is really what you're interested in most of the cases, runs, then starting at the bottom, you have some hardware, some metal that exposes or can be used through a certain ISA. So depending on the architecture, ARM v8, x86 64-bit, RISC-V or whatever, you have an interface there, and that is ISA. You typically also have an operating system layer. That is not always the case. If you think about certain microcontroller environments, whatever, you might be directly working on the metal, and Rust is really good at that if you think about it. However, very often if you think about a virtual machine in AWS, for example, you do have an operating system such as Linux or GNU/Linux, Windows, etc., that you're typically programming against, and there is a BI, a binary interface there. On top of that, you will typically find libraries, libc, musl, etc., and your app might go through that library, might do syscalls through that library, might directly talk with the hardware. But this should give you an idea that there are quite some moving parts there that you need to consider. Now, moving on to the entire life cycle, as a developer starting on the left-hand side, you have, in this particular case, I picked a containerized microservices setup. Obviously, that might look different if you're using Lambda or directly deploying on a virtual machine. So in this case, what you see there in that bubble or in that cloud there is in fact assumes containers, to be more precise, in most of those tools, Kubernetes. as the runtime environment, you create your artifacts, you create your binaries or whatever you have in addition and put that into repository. In our case, I would obviously use Amazon ECR. And then the runtime environment, in this case EKS, which is a managed Kubernetes service that we are offering, runs on a certain hardware again. In this case, I picked Graviton2, our ARM-based offering. And the repository is kind of like the handover between your development space and the runtime environment, and that EKS cluster, more specifically, technically the kubelet through the container runtime interface on each of those nodes would then pull, for example, a container image and run that for you. And last but not least, there is also this feedback cycle, closing that, the arrow number 3, giving you metrics, observability, could be trace, could be logs, output, whatever you have that informs and helps you developing new features or fixing bugs. So the question here really is, any given programming language, does it actually support the entire lifecycle? So let's have a look at the state of the art. Obviously, I'm talking about Rust here. So if we look at the Rust-C documentation, it says Rust-C is a cross-compiler by default. So that's cool. That's awesome. And essentially means by using the target flag, you can specify a certain architecture, certain ISA, and your binary will be created for that target. So that's great. And it also mentions a few target features, some notes there concerning the 2 popular CPU architectures, ISA x86 and ARM v8. And so up to this part, I would say everything is hunky-dory, everything is great, you're prepared. If you dig a little bit deeper, and please note that's nightly docs there of Rust-C, you have certain tiers. So in a sense, SLA, SLOs around how certain platforms are supported, be it in terms of the architecture or in terms of the host. So there you see, by and large, x86 is supported, fully. Tier 2, that's where it's getting interesting, includes ARM, right? And a lot of ARM things there. Obviously, there is a lot of variation in terms of targets, anything from ARM64 iOS to Android, Windows, Linux, etc., etc. And note that not always you necessarily have an operating system there. Some of those, like picking a random one, ARM64 Linux for a certain kernel, you can also, use the host there. But, it's tier 2. It's not tier 1 yet. And then there's tier 3, and the lower you get there, the less awesome the support is, if you wish. And this is certainly something where I'd like to, call for action. Really, I'd like to call you as a community out there to see if we can improve the situation there. Can we move more into tier 2 or tier 1 eventually, and what is necessary there? And given that most of the other parts in the life cycle, if you remember back early on, things like container registries, for example, or runtimes such as Kubernetes, are multi-architecture ready. Obviously, it is super important that the programming language of choice, in our case, obviously Rust, supports at least the most popular, most widely used ISA, the most widely used architectures out of the box fully. All right, so with this call for action, I'm wrapping up, and I hope that we can start a conversation really now based on what we've learned, and now that we're all on the same page, let's have a look at what needs to be done to make the multi-architecture application development with Rust awesome and comprehensive. Thanks a lot.